Okay, welcome to the last day of ST4 2020. We have two lectures today. The first lecture is going to be Adwait telling us about information loss in ADS2. Over to you, Adwait.
Okay, thank you. So let me just quickly remind you guys what we saw in the last lecture. Um, we had imagined the space-time where eternal black hole is coupled to the bath, and it's exchanging energy with it. And I described how the space-time can be embedded in 2D flat space. In the sense, the metric on this hybrid space-time is conformally equivalent to a 2D flat space. I also describe what is a particular state that you need to prepare such that the black hole remains in equilibrium with the bath. So the stress tensor on both sides have to be exactly same. Then then the strategy was to do all the computations in. So first of all, the black hole or the horizon geometry in ADS2 gravity uh, is a vacuum solution. So in the x coordinates, which is this Poincare wedge here, the Poincare wedge is described by x coordinates. You want to keep your stress tensor to be 0. So you keep your stress tensor 0 in x coordinates. Now you know a coordinate transformation from the W to X, and W describes the diamond. So W describes the flat 2D diamond. Okay. X coordinates describe the Poincare wedge. The Y coordinates describe the external of the black hole, exterior of the black hole, exterior of black hole plus the bath, right? So the region and this exterior of the bath plus black hole is in this diagram is green region plus the red region. Okay. So if you impose the condition that the stress tensor in x coordinates is 0, you from the coordinate transformation you can find out that the stress tensor in w coordinates is also 0. What does that mean? That the red line here, the all along the red slice here, the stress tensor is 0. That means we are really considering vacuum in w coordinates for the CFT. So I'm putting a CFT all over this manifold. Now from w coordinates you can go to yr coordinates, which is the right Rindler exterior, and I had given you the coordinate transformations, and that is just a conformal transformations, and you know how to find out stress tensor change under conformal transformation. It's just the Schwarzian piece, because original TW is 0, so the only thing you get is the Schwarzian piece. And then there are some non-trivial wild transformations that you have to do differently on the green and red region, and you have to make sure that the wild factor matches across the boundary of these regions. And these wild factors are nice such that they don't pick up any wild anomaly. So the only contribution that comes to the stress tensor in the exterior of the black hole is only from this conformal transformations, and which can be easily computed. So we did that, and after that I showed you how we did this computation. The computation was supposed to be of the radiation of the Hawking radiation. So in the 1D model, which I have described here, okay, this is a 1D point of view. In the 1D point of view, I wanted to compute entanglement entropy, a fine-grained entanglement entropy, which I have written here, of minus infinity to minus b union b to infinity. Okay, and the coordinates the coordinate systems for 1D are the left system has YL coordinates, and they go from minus infinity to 0, and the right system has YR coordinates, which goes from 0 to infinity. And this bracket is YR equals to b, and on the left it's YL equals to minus b. So I should put subscripts to this. So this the minus infinity to minus b interval is in the left system, and b to infinity is in the right system, and I'm computing the fine-grained entropy in the sense. So one thing is that the only thing that we know for sure, and we know the physics of completely, is the 1D system, because 1D system is just a simple quantum mechanical system. There is a CFT1 which which sits on these dots, and then there is a CFT2 which sits on these lines. Okay, and we know how to handle these objects, even though it might be complicated how to couple CFT1 to a CFT2, but in principle everything is known about it. Something might be fishy with gravity, but whatever we compute in the 1D system has to be perfect. So I want to compute a fine grained entropy in the 1D system, and that is equal to, so it's dual to doing a fine grained entropy computation in the bulk by just the holographic dual. So what is the holographic dual? I just replace the dots by the interior of the black hole. Okay, and in that is equivalent to doing the fine grained entropy of BL union BR. So right now we are not using any Rutag prescription, and we are just following our nose and saying, "Ki, okay, this seems fair computation. This seems like the thing to do. So let's compute it." So the bath is where the radiation is escaping. So radiation is escaping on the both sides of the black hole because it's a two-sided black hole. So in order to compute entropy of the radiation, I consider two intervals which are on the both exteriors, and I have called them BL and BR. So I want to compute fine grained entropy of the BL and BR in the bulk. Okay, and by unitarity, so the slice I have drawn here, the blue slice I have drawn in the diagram, assume that there is a pure state all along that slice. So if it's a pure state all along that slice, then the fine grained entropy of BL union BR has to be equal to fine grained entropy of LR, where LR is I'm calling the middle region as LR, which is holographically constructed from the 1D CFT. And we did this computation, and we saw that this result is always growing in time, and this is the ever growing entropy result, which contradicts with unitarity, because what will happen is you'll see that what is happening. We are saying that the entanglement entropy of BL union BR is growing. Okay, so it has to be that by unitarity it has to be that the entanglement entropy of LR is growing. But LR contains a black hole, and black hole has a bound on degrees of freedom, which is just the entropy of the black hole. So the entanglement entropy of the BL union BR cannot grow more than the coarse-grained entropy of the black hole, and that's where the problem is, which is the entropic information paradox. And this is just the same computation that I just made in a particular model. I have made a constructive honest to goodness computation to show that yes, if you do a naive calculation, you get a wrong result. And this is a similar result to the n log 2, which I kept on talking in the previous lectures. So yeah, so let's start today's lecture where, okay. So one thing I wanted to point out is that just to understand our previous result of linearly growing entropy, let me look at this diagram. And what is happening is that we are computing this entropy. So yeah, so there is a particular curve here, which is y1 left equals to minus b. There's a curve here, which is y1r equals to b. Okay, and then we had considered some slice, and we are considering some slice here. Okay, so now these points here, maybe let me. So these points here, okay, so this point is basically in the y coordinates, yr coordinates, this point is t comma b, and this point in the yl coordinates is t comma minus b. Okay, and what is happening is that we just wanted to compute entanglement entropy of the region LR. Okay, and this is BL and this is BR. Okay, so now I know that in the W coordinates, which is just the ground state, in the W coordinate it's a ground state. So W coordinate is, that means it's the diamond which does this. It's a diamond which can be extended like this. In the W coordinates, the formula for entanglement entropy is just c/3 log of L divided by epsilon, where L is the length of the interval. Okay, this is the entanglement entropy formula in 2D CFT in its vacuum. Okay, so if this is linear, okay, so we computed this in W coordinates, and we saw that this comes out to be linear, which is the result I showed you. But you have to do so basically what you have to do is you have to transform YL equals to t comma minus b to w. So you have to find out what this point is in the w coordinates, and then you also have to find out what yr equals to t comma b means in the w coordinate. Okay, so let's call this w1, this point as w1, and this point as w2, and then just find out what is the length, what is the length of w1 minus w2. Okay, in flat space.
I
And if
think
you,
Subbu has a question.
yes.
Yeah, so this I missed in the last lecture. I mean, it skipped me. So this, are you considering like a zero temperature CFT in this 2D space time?
So yeah, so this was this whole discussion about stress tensors. So first of all, in the Poincare coordinates, the black hole solution is a vacuum solution. So Poincare
I see.
coordinates were x coordinates.
Okay,
Hence, in x coordinates, it's vacuum. So that
Okay.
is what I have to impose everywhere. So what
I see.
happens is if I impose that it's a vacuum in x coordinates, then it becomes vacuum in w coordinates.
Okay.
So it's tx is 0 in, so when I say t, it's plus and minus components. Okay, so it's 0 in x coordinates, so it's and by coordinate transformation you'll see that it's 0 in w coordinates also. And then you can find out exactly what it, because you have to do conformal transformations to go to y coordinates, then you'll see that it picks up some value, but it's fine because it's supposed to be understood as exterior of a black hole. So
Okay. So it has temperature in that coordinate.
in that region, yeah. In y coordinates it has temperature, but in the bigger coordinates, or w or x, it doesn't have. So
I see. Okay, all right. Okay, yeah. Now I remember. Yeah. Okay. Yeah. Thanks. Yeah.
Karan, go ahead.
Yeah, I think I also missed something in the last lecture. So you've got a region which has curvature and one region which does not in the y coordinates, right?
Yeah.
So how are you imposing that? Just through the factor, through the overall
the
factor?
Weil factor, that's it.
The Weil factor provides the curvature in one and not in the other.
Yeah.
Okay, thanks.
Okay. So all you had to
Akhil has a question. Akhil, go ahead.
Yes.
Hi, had you said that the y coordinate vacuum is a thermal state in x coordinates, or did I mishear that?
Not
Did you
thermal, it's a TFD.
Yes.
I mean, it's a
So
one.
it's-
It's a yeah. It's a
So,
one.
sorry, I thought just now to Subbu's comment you said it's a vacuum in both y and x coordinates.
It's vacuum in x and w coordinates. It's not a vacuum in y coordinates.
Oh, okay. I see. Thanks. Okay.
I mean, it's an excited state, but it's an excited state in the same vacuum module because it's just a conformal transformation. You're just acting by lns, with our sort of generators. So so all you had to do was take these points y of t comma minus b and y r as t comma b, transform them to w's, and find out what is the length between these 2 points w1 and w2, and you'll basically see that the length of this bridge lr keeps on growing exponentially. So it has to grow exponentially, right? So this L has to go exponentially, then the log formula will automatically give you linearly growing result. Okay, so this is just a physical intuition to say that the bridge in here keeps on growing exponentially, and that's the reason for the exponential growth in the w for exponential growth in the w coordinates. And if you go to if you just plug this formula in your if you plug exponential in this formula, you'll get a linear growth of the entanglement entropy. So this is just a point because I'll use this result at some point again, it grows, this bridge grows. Okay, so now let's use the modern technique that we know. So what did we do before? So we had a system, and now I want to start color coding things. So if it's yellow, then that means I'm just talking, I'm writing quantities in 1D CFT, in the 1D point of view. Okay, so in the 1D point of view, you have a line and a dot here and a line and a dot here. Okay, where there is a CFT1, a holographic CFT1 here. Okay, and a CFT2 at these on these two, a CFT2 on a half line. Okay. And then what we did, the computation we did of the linear growth was we were trying to compute entanglement entropy of these regions. Okay. And what are these regions? So this region is minus infinity to B in the left system. And this region here is B to infinity in the right system. Okay. Now, and we computed, and this, so basically the fine-grained entropy, we computed fine-grained entropy of minus infinity B left union B comma infinity right, and we saw that this is just ever growing. So we saw that this goes as T, okay, when beta is much less than T in this system. Now, instead of doing this computation, let's try to do the other computation. The other computation is basically this, which we expect to be exactly the same by unitarity. Okay.
Hi, can I ask something?
Yes.
This t is the time measured by in y coordinates, right?
Yes.
In the Hawking calculation, the analogous the correct statement would have been it grows like the time of the x coordinates. Isn't that right?
No, the exterior coordinate.
Which was x coordinates, right?
No, x coordinate is a Poincare coordinate. Let me again try to tell you what coordinates are what. So
in the green patch, right? The time coordinate in the green patch.
Yeah, that's
Which
y
was,
coordinate, right? So y0 is what I'm calling.
Oh, right. W is the whole. Okay.
Exactly. So W is the whole 2D flat diamond. X is the Poincare wedge, and Y is the exterior of the black hole plus bath.
Yeah.
Okay. So let's try to do the other computation. The other computation is just this, where the interval here is B to minus B to 0. So okay, I should have put a minus sign here. Sorry, minus B to 0, and union on the left, and union 0 to B on the right. Okay, this is the computation I want to do, and let's try to do this computation using the bulk. Okay, so let's first of all, I would like to say that this is a slightly okay. Just consider a limiting case of this. Okay, the limiting case is B going to 0. Okay, what are we doing in B going to 0? In B going to 0, we are just saying that I am going to compute entanglement entropy of just the dot, right? I'm almost shrinking that interval to 0, such that I only want to compute entanglement entropy of this holographic CFT1. Okay, and I know how to do that, right? If it's a holographic CFT, I just use the quantum Ruta-Kanagi prescription, and that's what I do. Okay, so let's try to do that. And this, so as I said before, that there is no subregion in this CFT to consider, right? Because it's a 0-dimensional space-like slice. It's just a point. So that's why this particular limit that I have just included a small piece of bath is just important. It's not really that necessary, but it's for understanding. And if it confuses you, you can always take B to 0. Okay, where you're just computing entanglement entropy of the holographic CFT. So let's go ahead. Okay, so let me just add this. Okay, so this is what we're doing. Now consider that consider a particular time slice somewhere in your somewhere along your CFT1. So let's say I'm considering this particular time slice. Okay, and let's take the same time slice on the both sides, and these dots are supposed to represent CFT1. So remember that there is either a 1D point of view where there is CFT1, and either there is a 2D point of view where there's gravity and no CFT1. But this is a diagram where I'm just drawing it hybrid, in the sense that these dots are the same as whatever is the geometry inside. Okay, so let me first, so as I said, the quantum RT surface is a codimension 2 surface to the bulk. Okay, so the entanglement wedge, this formula is a homology constraint. Now let me write Okay, so should be, so I'm considering all of CFT. So, okay, let me still call this subregion as B. Okay, so let me call it A. So this is AR and this is AL. Okay. Oh, sorry. Just call it L and R. The left system and the right system. That's a better notation. Okay. So this is the notation. So what should happen is that the boundary of the entanglement wedge should be L union R union the extremal surface. Okay. This is the formula that I had given before. Is that so? Let me just go back to that slide just to indicate what I'm saying. So look at this slide here. So I said that you are considering the subregion B here. Okay, this is a subregion B, and we construct all possible chi's such that chi union the boundary region has to be the boundary of the entanglement wedge. What does that mean? That means that chi as a surface, chi and B as two surfaces trap a region inside it, and that region is what we call entanglement wedge. This also means that you should be able to continuously deform chi, which is this surface here, You should be able to continuously deform chi to B, which is the boundary region. Now the point is, in our case, there is no boundary subregion, so we are really considering all of the subsystem, like all of the system. So you are really taking all of this region and constructing quantum Rutag-Yanagi extremal surfaces for them. Okay, so I'm going to claim something and then I'm going to justify it. So here L union R is a zero-dimensional system, right? These are just two dots, so it's a zero-dimensional system. Entanglement wedge. So this is also a zero-dimensional surface, right? So L union R is also zero-dimensional. Chi is also zero-dimensional. So entanglement wedge is one-dimensional. What does that mean? So let's consider a test surface. So let me put let's say I put a quantum extremal surface chi here. Okay, so let's call this chi, and let's call this chi L. And let's put some other surface here on the both sides. So first of all, the things would be symmetric on both sides. So whatever is on the left, it'll be almost symmetric on the right hand side also. So let's call this chi R. Okay. So now these 2 points are your extremal surfaces. As I said, extremal surfaces are going to be zero-dimensional objects. Hence, they are points. Okay, and they're codimensional 2 to the bulk, where bulk is 2D. And now, what is the entanglement wedge? The entanglement wedge is going to be a surface trapped between these two, right? So a surface trapped between these two regions is basically a line which is one-dimensional. Okay, so let's say you get a non-trivial quantum extremal surface chi, then the surface should look like this. This is how the construction should look like. Okay, so if I want to be let me just give more notations. So let me call this region here as sigma chi L, which is the entanglement wedge of the left system. And let me call this system as this segment as sigma chi R, and which is the entanglement wedge of the right system. Okay. So first of all, this is not the only thing that you have to satisfy. You have to also do the extremization problem. Okay. You have to extremize over this chi L and chi R, and where the place where it extremizes, that will compute your fine-grained entropy of the interval of these two intervals, the 0 comma minus b comma 0 and 0 comma b. Okay, so that's what I'm trying to do. So first of all, let's just consider this one as a contender. So let's say this is a contender for your extremal surface. Okay, and but there's one more kind of extremal surfaces which is generally always available, which I'll just add it here. Okay, which is this. So let's just consider homology constraint first. Okay. um what do I have to do? So let's consider the extremal surface to be a null set. Okay, so this is not a null surface as in surface along which null rays go. It's a null set. Null set means there is no surface. Okay, there is no surface in the bulk. What does that mean? That means that if you have these 2 points as your system, which is these 2 points are just, I'm not sure what's happening. Just a minute. Maybe let me just go to the next page. Because, okay, so let me just draw it here. Let's consider these 2 points as your L and R system. Okay, and what I said is that you want to choose chi as a null set. Now let me explain what does that mean. That means that so what was happening in the previous diagram was that when we were considering some extremal surfaces in the bulk, right? These were the chi L and chi R, which I have pointed in this diagram, are some extremal surfaces in the bulk. Now, what it means to have null set, that means that your entanglement wedge just goes across. It just goes across left to right. Okay, and I'll just call this as sigma, sigma phi, sigma of the entanglement wedge for the null set. So are these 2 contenders clear? In the sense, first I'm saying that you could have some non-trivial quantum Ruther-Genagi surfaces, which I have drawn here. So the small green circles are those surfaces. But there is another possibility, which is a null set, and let's see whether the null set satisfies the homology constraint, and it does. So what does that say? It says that, so maybe let me write it on the next slide. It says that the boundary of the null entanglement wedge, which is this straight line, should be equal to L union R union your extremal surface, which is chi, which is basically your null set. Okay, so this equation is true, right? Because this is a 0-dimensional thing, and this is a 1D thing. Okay, and this is just nothing. This is just null. Okay, there is no surface, in the sense that if I write down an S generalized. Okay, so let me if I write down an S generalized, what will I write? So, okay, one thing is that I think I had written S generalized before, and I don't remember what I exactly wrote, but okay. So S generalized before was area of chi divided by 4g Newton plus S bulk, which is, so S semi-classical, in the sense it's a von Neumann entropy of the semi-classical fields on the bulk slice sigma chi, which is the entanglement wedge of your extremal surface. Okay, now you would say that, okay, this is a 2-dimensional surface where the subregion or the region or even the extremal surface are all 0-dimensional. So what does it mean by area? Okay, so I'll just tell you a fact, and you just take it as a face value. Believe me that this happens, is that in 2D dilaton gravities, the area is replaced by the value of the dilaton. Okay, so in high dimensional systems, let's say if you want to compute black hole entropy, you would compute area of the horizon. In 2D dilaton gravity, you would compute the value of the dilaton at the distance of the horizon. Okay, so the horizon, so the area is exactly equivalent to the value of the dilaton, and this can be understood in when you do a high dimensional reduction. So let's say you do a reduction from a 4D black hole, and you will get ADS2 cross S2. So S2 is this S2 is basically a spherical area, which exactly gets interpreted as dilaton for the so that S2 becomes dilaton. And people who must have studied colors of plane reductions might know this, that this generally happens. The dilaton is really the area of the auxiliary space time, okay, which is some compact space time. So in this, so now in the 2D dilaton gravity, how will I write? So let's say the okay. So let's say in the y coordinates, the extremal surface is given by, so let's say this point is something like a in the y coordinates, and this point is something like minus a. Okay, these are all, so this is in y y l coordinates, and this is in y r coordinates. Okay, so what will I do? So when I have such a contribution, you can see when I have such a extremal surface, which is on this slide, this is what I should write. So S generalized is a function of the extremal surface. Extremal surface here is just given by a. Okay, in the sense the only parameter to extremize over is the a. I have to vary a. So in principle, I can vary in time also. So really the right. So it should be really something like a comma t, where I vary both of these parameters. But I'll not tell you. Okay, I just believe me that the extremal surface also lies on the same time slice as the boundary. So if my boundary L system is at a time t, my extremal surface is also at a time t in y coordinates. Okay, this just happens, and you can verify it later. But I just want to do extremization in only one parameter. That's why I'm just reducing the parameter. It's for simplicity. So S generalized is going to be a function of a. So a is the only parameter I have to extremize over. So it's the value of the dilaton at a. Okay, but there are two dilatons, right? Because there are two extremal surfaces. There is chi L and chi R. So it's twice of that divided by 4g Newton. Okay, and you'll see that the value is symmetric on both sides. So putting phi a and phi minus a is the same thing. Plus a fine-grained entropy, which should be computed in a semi-classical physics in a fixed background of okay, of what? Of sigma chi L union sigma chi R. This is what I'm supposed to do. Okay, this is what should give me the fine grained. So this, what is this? This is a fine grained entanglement entropy of the system L comma R in the one dimension. So this is if I after extremization. So I have to, so SF of a system L union R, and L union. So whenever I'm writing in colors, it's a 1D quantity. So what does that mean? That means that I'm taking these. I'm taking this B going to 0 limit here. Okay, that means I'm just taking the system L, which is this, and system R. Okay, so I take LR system, and I want to find out fine-grained entropy of those systems. And what I do is that I have to minimize. So first extremize, and then minimize the S generalized of A, where A is given by the formula that I've written before below. So I'll stop for a minute, and please, if you have questions, to ask.
A couple of questions. Rohan?
The dilaton is constant in the gray region, right?
In the gray region, let me see. So in this, dilaton is constant? No, it's not constant. It's a running dilaton.
It's what?
It's a running dilaton, right? It grows towards the boundary.
Oh, this is not the extremal value then.
No. It
is the fluctuation over it.
Yes.
Okay, thanks.
Yeah. Any other questions? Good.
Karan had a question.
Karan has a
Yeah.
Yeah, sort of related, but like in that diagram, how are you finding chi R and chi L, or is that what you're going to turn to next? Like, how are you showing that the surfaces are actually not going all the way to the center, but rather are stopping at chi-r and chi-i?
No, right now I've just written a contender. Okay. And then
Okay.
I have to do the extremization problem over A. So this
Okay.
min and x, these things have to be still done. I've just written
Okay.
down a contender thing, and there are two contenders. One is that there exists a non-trivial quantum Rutha-Kanagi surface, which is just given by A, or there doesn't exist, which is the null set case, which I was describing before, right? Which is basically that you just go here and okay, not this, sorry. So you just have 2 points, and what happens is the entanglement wedge just goes across, and there is no extremal surface. It's a null set.
Okay. So you will show why we get those two points for L and R.
I mean, I'll just show that the extremization problem has a non-trivial solution. I won't do the I won't find the solution. Okay. So
sorry, I have a couple of questions.
Yeah.
So firstly, this null set, when you're taking chi equals to null set, is it possible to generalize this to higher dimensions as well? I mean, how would I visualize this in higher dimensions?
So yeah, it's just that just consider. So maybe are you okay? I'm not sure if so. There's this paper by Malus and Hartman. Okay, what they do in that paper is they construct a 3D gravity with two 2D CFTs. Okay, so consider there are two CFTs here. This is a one plane, and this is one plane, and these are 2D CFTs. Okay, so time goes up, and horizontal directions are x directions, and in between the black hole is formed. So let's say this is the left CFT2, and this is the right CFT2. Okay, and what they do is they basically say, let's take an interval, and let's take an interval here, and let's call whatever these intervals are, and then compute entanglement entropy of union of these two intervals. Okay, and they get two kinds of Rutha-Kanagi surfaces. So that's a Rutha-Kanagi competition, not quantum Rutha-Kanagi competition. So one kind of a Rutha-Kanagi surface they get is just a geodesic hanging inside and comes back. Okay, and the other kind of Rutha-Kanagi surface they get is the geodesic which just connects across. So maybe I should draw a little bit more slanted line. It just connects across. Okay, so like these are the boundary regions of which entanglement entropy we are computing. Then there are two contender surfaces. One is which hangs inside, and the other which just goes across. Okay, now imagine a limit where you take these surfaces to cover all of the space, in the sense to cover all of this line. Okay, complete line on this 2D CFT. If you do that, you'll see that this Rutha-Kanagi surface still has a probability that it will start from, so let me try to draw some similar diagrams. So let's say I'm taking the complete theory, then the above diagram still happens to be like this, that there is something that goes in and comes back, and it just at the ends of the theory. But the below thing, what happens is, okay.
It will just take up the whole spatial
Exactly.
space.
So, and because these two lines which I'm drawing are just for drawing there, they really are pushed to infinity.
Right.
So these lines just don't exist. So that is equivalent to having a null set.
And another question is that in the expression for entropy, when you have replaced the area by the value of the dilaton at that point, do we still know that the semi-classical part of the expression is still subleading to the first one?
Because the semi-classical part of the of this expression is order C, right? Because it's coming from a 2D
right. Yeah.
And then the area contribution is 1 over G Newton. And as long as I'm working in a limit where 1 over G Newton is much greater than C, I'm done. Okay. So that's okay. So all right.
I have slight confusion about this null set case.
Yes, please.
So I thought in black when you calculate the RT with RT surfaces with black holes, you end up having a surface which just hugs the black hole, and you include that.
That's the RT, not necessarily quantum RT. QRT has this, so QRT has this second term, semi-classical or entropy of the entanglement wedge. That makes a difference in extremization problem. So if you just do an extremization using the area term,
I thought that came really from being this homologous and such conditions, right? So I'm slightly confused because now you have now you're calculating the entropy of just the exterior, but it really goes through the black hole, isn't it?
Yeah.
I
No,
thought
I'm
I'll have
not.
to
See, I'm computing entanglement entropy of L union R. L union R are holographic 2 points.
Okay.
Which are just these 2 dots. I'm just doing this B going to 0 limit.
But am I still allowed to go? I can't really calculate the fine-grained entropy of fields inside the black hole, right?
Why not?
I mean, I'm just asking because your null set surface really went through the black hole.
I basically did it here, right? In this computation, I did it here.
So you really calculate you really look at the field content inside the horizon and calculate its fine-grained entropy.
Yeah.
Why am I allowed to do that?
I mean, why are you not allowed to do that? People didn't do it
maybe
because they couldn't do it. I think.
Maybe I'm confused because I thought the whole situation is really because you can't measure the fields inside the horizon and you can't hence calculate the entropy.
I don't think that's true. You can do it. I mean, I did it in this computation basically. I did the computation in W coordinates and then transformed it back to Y coordinates, which is like doing a computation in a black hole background.
Okay, thanks.
Nice. So, okay, now let's write down a Ruth-Akanagi prescription for this also. So how will you write it down? You'll basically write down S generalized. First of all, so you don't really have to do extremization problem in this because there is no there's nothing to extremize over. Okay, so you just write down S generalized for your null set, and that is, first of all, the first term is the area of the dileton. Okay, but the value of the dileton at the extremal surface, but there is no extremal surface. So let me write down that term, but that term is really, so the dileton at some null value, okay, which is really just not there. Okay, it's just 0.
Can I ask another question?
Yeah, go ahead.
So can you think of it as,
just let me complete this argument.
Okay,
then
sure.
Then the second term is that this system was L and this system was R. I'm sorry for changing notations a lot, but it's sorry. And now let me call this as the entanglement wedge of LR. Okay, because there's no chi really. So I just have to find out S bulk of, so this is a fine-grained entropy computation in the semi-classical limit of the gravity on the sigma LR system. Okay, so this is what we have. And so first of all, we got this. Let's say okay, so first of all, we got this, and let me write down these 2 contributions. So what did we have? We had an S. We had 2 kinds of Ruth-Akanagi surfaces, 2 kinds of surfaces, quantum RT contender surfaces, which is twice of G Newton plus there's an S semi-classical, okay, which is minus B comma A on the left, union minus A comma B on the right. These are these 2 segments. And another kind of contender that we have is just S, sorry. So these are fine-grained entropies. S fine-grained of semi-classical fields on just the region sigma LR. Okay. So these are the 2 contenders, and the principle tells us that the fine-grained entropy of just L union R, maybe different color, fine-grained entropy of L union R. So this is something that should be computed in this model. Okay, So there is this model where I'm just computing entropy of these dots. This is equal to, now I have to do an extremization principle, and let's say I find an extremal A. So I have to first of all extremize over A in this formula. Okay, let's say I do that. There is no extremization to do in the second formula. Okay, the first formula, S generalized of A, is where extremization has to be done over A. Let's say I do that, and then what I have to do is I have to minimize over all possible surfaces. So the final formula boils down to this. It's just minimum of S generalized phi, comma, S generalized over A, but it's an extremal A. So I have done the extremization problem. Let's assume I have done the extremization problem and I get this. So this is the final answer. Okay. Now I will stop and please ask a question.
Yeah. So can I ask something?
Yeah.
Yeah. So so when you say the phi is the S-gen of phi, did it mean that there is no extremal surface where the coordinates are real, or does it mean that there's no solution at all?
No, there is nothing to extremize over. It just
I'm asking. There will be some equation for the extremal surface, and you end up.
That's what I'm saying. There is no equation for the extremal surface because I've chosen there is this null set as an extremal surface is a perfectly valid surface which always exists, which is always there because it follows the homology constraint. Okay, but it's just that in most cases, for example, in this in most cases you will find that is not the answer because it's probably bigger than all other possible contenders like A, but it's a trivial surface which is always available to you. It's always there in all the extremization problem that you would ever do. A null set is a available surface. Okay, and you don't really have to extremize. Okay, it's if there is no other surface, then null set is the only surface that you have.
Okay.
Okay.
Karan had a question. Karan, go ahead.
Yeah, just two questions. I not too pressing, but anyway. So the first is that when you go from X to Y, are you going from some kind of one-sided setup to a two-sided setup in the sense of the X is just pinching off on the left side?
Yeah.
And then, so you can view that as a one-sided thing with no temperature. And then when you go to Y, you have this two-sided thing with temperature. Is that what you're doing?
No. So X to Y. When I'm going X to Y, more precisely, I'm going from right Poincare wedge to right Rendler wedge. Okay. I can similarly define left Poincare wedge and left Rendler wedge, and I can do the exact same transform. The transformations would be different, but it's the same construction. I'm just doing the construction for only one side.
Okay, so when you do it for two sides, then you end up with this proper thermophile double sort of setup.
Yeah, exactly.
Before that,
so
you just end up with one. Okay.
The coordinate patch which covers two sides is the Kruskal patch, Kruskal coordinates.
Yeah.
Okay, and the ground state of the Kruskal coordinates is the same as Poincare ground state. Okay, so this is something that I haven't said before, but if you create a patch where both where all the both exteriors are considered, that is the Kruskal patch, and the ground state in Kruskal coordinates is the same as ground state in Poincare coordinates, left or right, whatever you want to choose.
Okay. And the second question I wanted to ask was, so in the standard thermophile double case, this would be viewed as some evolution. This null set that you're calling would be some evolved state of the thermophile double state. Does it have a similar interpretation here, or are there any subtleties?
Say that again. I didn't get the question. Sorry. I think we lost him. Yeah.
Hello, can you hear me?
I lost you. So just ask your question again.
Yeah. So I was asking if in that null set extremal surface which you've drawn,
yeah,
is it exactly analogous to the time evolved thermophile double state that you would have in the thermophile double construction, or is there any subtlety here?
I mean, it has nothing to do with the state. It's just a possible extremal surface. That's it.
Yeah.
Right?
So what I'm asking is it the evolution from the t is equal to 0 surface? Is it simply that?
Oh, you mean is it the same surface that would have been lying here?
Yes.
I mean, you just take a surface which goes across, and that's the same thing. You mean is it
I'm
evolution
asking
of this
whether you
surface?
can evolve that to that. Yes, that's
Yeah,
exactly what I'm asking.
yeah. I mean,
Okay,
I don't know what do you mean by evolve. So it's there's no
I mean,
equation
you
of
have a
motion for this
Hamiltonian on the
surface.
left and the right, and you would evolve this y0 to yr, and same on the left side with the left Hamiltonian and so on. That's what I mean. Anyway, yeah, thanks.
Extremal surfaces are not some dynamical objects, right? They come as a result of some extremization problem or some problem. It's the contender surfaces for computing something. These are not dynamical objects. So I don't know how you evolve an extremal surface using some Hamiltonian.
Just a quick short point here. So I mean, you'll evolve it and then extremize. So you would evolve from, let's say, the 0 surface to yr, yl, and then extremize.
At every time you have to find an extremum.
Right.
Okay.
Right.
So now
Thanks.
the another statement I made sometime before is that the null set is always available, but it's always available if you are considering all of the field theory. Okay. As in this case where we are only considering in this case where I've drawn this diagram on the right hand side, we are only considering parts of space-time. We are only considering sub-region. Then the null set is not a contender at all. But when you're considering all of the field theory, which is the lower diagram, the null set, the two lines which go across become the null set surface. Okay. All right. So we are here now, and let's see. Let's just look at this formula for a while. These two contributions, the S fine grained semi-classical, are order C contributions. Okay. So so it's clear that at least at early times, okay, when at the time dependent entanglement, the part of the fine grained entanglement entropy is small or order 1, and in the limit where 1 over g Newton is much greater than c, you can clearly say, so let me write down at early times S generalized A is clearly bigger than S generalized of the null set. Right? Is that clear? Because S generalized of A has of A extremal, let's say, whatever extremization problem you do of A extremal is clearly has a 1 over g Newton piece, and 1 over g Newton is much greater than C. Hence, it's definitely greater than S generalized of the null set. Okay, so now we know that the minimization problem, at least at early times, just in the minimization problem, just S generalized of the null set wins. I'll stop for a minute to just for you to grasp this thing, but all I'm trying to say is that S generalized, the non-trivial Rutha-Kernaghi surface A has a 1 over g Newton piece and a time dependent piece, but time dependent piece is order C. Okay, and the trivial Rutha-Kernaghi surface, which is the null set, has only order C piece. So at early times, clearly the null set is the extremal surface, which is the null set, is the winner. Okay, hence at early time, the actual answer to the extremization problem, which we have written down here, the extremization problem which we have written down here, or extremization and minimization problem, is this surface. Okay, and we have computed what is the entanglement entropy for this surface. This surface, the entanglement entropy for this surface just linearly grows. Okay, which is completely fine for early times, right? Because how does in previous lectures I had shown you how does the page curve should look. The page curve should first linearly rise for an eternal black hole, and then it should just settle down at a value of a black hole. So should just settle down at a value of a black hole. But what happens is, the problem is that the way we just computed this for all times, right? So the computation that was done here of LR here, which I should have really called sigma LR, but as LR here, just keeps on growing linearly. Okay, and that is a problem only after the page time, and page time is a point. So it's a problem only after this point. So first of all, this keeps on growing. It's a problem only after this time, because this fine-grained entropy, linearly growing fine-grained entropy, should not ever exceed the coarse-grained entropy of the black hole. So this is S fine-grained of the radiation. Okay, so at early times we have recovered the result that we wanted. At early times the entropy and the actual graph should look like this. So at the early time the entanglement entropy should be linearly growing, which we have, because we know that at early time null set is null set extremal surface dominates, and the computation for null set extremal surface is exactly same as Hawking computation, and hence early times it's a good computation. But you see, the argument which I made that 1 over G Newton is much greater than C has to break down at some point, because these pieces have time dependence in it. The C order C pieces have time dependences in it. Okay, and at some time the time dependence is going to grow such that this condition which I have written here, which is only valid at early times, must break down. Okay, and when it breaks down, at that point S generalized A is the minimal surface. So this extremization problem has to be done at every time. Okay, and we see that this surface wins at early times. Okay, but now what you have to prove is that this surface wins at late times, and also you have to show that it doesn't just win. The fine-grained entropy that you compute from there, that has to be constant, and not just any constant. It has to be twice the black hole entropy. Okay, let me again stop for some time so that if you guys have some questions, please ask.
Shubham has a question.
Yeah, so like so this rising part, actually my question was about a physical intuition for this growth of phi, relative growths of phi and A extremal, but I think you just showed it in the next slide that you should identify the first part of the S gen phi with the growing part, and then so yeah, my question, I don't have a question.
This minimization condition is what causes the change. So it's a first order transition between the extremal surfaces. First, the extremal surface that you are considering is the null set, but later the extremal surface you are considering is this non-trivial surface, which the extremization problem I'll do. Okay.
All right.
Rohan, go ahead.
Yeah. So since you're using near extremal geometries, this analysis should only be valid in the beginning and the end of the page time, right? I mean, the beginning and the end of the page curve. Because you're looking at small black holes and you're using.
You're saying that the transition will not be sharp. There might be some different.
No. In the sense that you're using the fact that close to the horizon there is an extremal ADS2. I mean, there is an ADS2 near extremality, and that comes in quite heavily, right? In the whole analysis. And that can happen only for small black holes. So it's basically, you can say 1 over G Newton much greater than C or lesser than C only in when the black hole is small, which is happening when it is when it is just forming, or it has just formed, or it has just about to evaporate. But what is happening in between, as such, there is no extremal. There basically, if you have any black hole which is evaporating in the middle, when it is like quite big and stuff, it will not have, in general, an ADS2 throat. So, but the argument still goes through. But then this last point that you said that constant should be twice the black hole entropy at the page time. In the curve, so that middle part of the curve where you actually see the rise and fall of the actual entropy, that may not be captured, right, in this model at least. You can't do any matching as such. That's what. How is that coming out then?
Probably. Let me go ahead.
Sure. Okay.
To say, yeah. Actually, I'm also forgetting whether there is an exact matching or not. But I just know that this feature of exact sharp transition is not really true, in the sense it's only coming because we are only considering Ruther-Kanagi formula up to leading order. So if I just keep on adding subleading order corrections like the graviton and
yeah, but that's a different thing. I mean, that's a correction at the level of precision, coarse graining and stuff. Like, okay, actual thing might be lesser than the coarse grain.
Yeah.
So, but the model itself heavily depends on the fact that there is an extremal ADS2. That only happens for small black holes.
Okay, maybe.
Yeah. I mean, you can argue that C is much greater than 1 over G Newton at like late times, and like that transition of early times and late times goes through. You're saying that it is the black hole has just formed, or it is just about to evaporate. Yeah. So that way it goes through. But yeah. Anyways, I just wanted to clarify a bit.
Okay.
Thanks.
So yeah. So let's look at.
Yes, Karan. No, sorry. Go ahead.
Okay. So now the thing is, I was explaining that the dot is here, and it's producing something in the middle, and you're computing entanglement wedges of them or extremal surfaces corresponding to those regions, and we were getting. Now I just want to generalize this setup to a bit more general setup, which is that let me not explicitly exactly say. Yeah. So now let me not say that I'm just computing. So what was happening earlier? Earlier I was saying that this is the limiting case that we were doing. That I'm just computing entanglement entropy of the dot to entanglement entropy between the dot and the line. But now I want to do something a bit more general, where I consider dot, but I consider a little bit more of the space also. Of the line also, which is saying that I'm considering intervals which go as -b, 0 to 0, b, and I'm not really considering b going to 0 limit. Okay, b going to 0 limit is, so this is b going to 0 limit. So let's do that. And that just, what does that mean? That just means that we are considering something that a surface which is just slightly outside. And hence this is, so let me draw 3 different surfaces. Okay. So there is a surface here. I mean, I'm just drawing a complete space like slice which goes through the bulk. So what happens is, this is the exterior part. Now you have an extremal surface somewhere here, and let's say there's an extremal surface somewhere here. Okay. And you also have this exterior part. So let's call this part as BL. Let's call this part as BR. Okay. Now, so before, what was happening was this dot here. So maybe let me go to the non-trivial. This dot here was equivalent to, and in the sense, everything in the dot can reconstruct operators in the line in this sigma chi L. Okay, so the left dot can generate operators, can reconstruct operators which are sitting in the sigma chi L, because it's the entanglement wedge of L, and similarly for R. So what I have done is there's a dot, and there's slightly I've attached a small piece of bath outside. All that does is that it just separates the region into, it just makes this as a region, okay, that you have to consider. So instead of starting from the vertical line, y equals to 0, I'm just starting a little bit outside, and then you can just consider, I don't know, yeah, you can just consider a region connecting these 2 points. Okay, now let's name these regions. So this region is what I call sigma chi L. This region is what I call sigma chi R. And let's call this region as island. Okay, so this is an island. Now what we showed is that, so keep in mind, we are still computing fine-grained entanglement entropy. Okay, we are still computing fine-grained entanglement entropy of minus b comma 0 left union 0 comma b in the 1D system. Okay, if this is the computation in the 1D system, that is equivalent to computing entanglement entropy of the dots, and that is equivalent to computing entanglement entropy of the black holes. Okay, and what did we saw? We saw that it captures that computation. So let me also put some circles here. Okay, because these are extremal surfaces, some non-trivial extremal surfaces, and what we saw is that the entanglement entropy of the okay, so let me write down an S generalized A, which is, okay, how do I do this? Sorry. So let me write down S generalized of A. What do I want to do? Okay, right. So first of all, the first piece here, S generalized A, as a first piece twice the dilaton, which is the area term. Okay, and the second term, which is what we have to non-trivially compute from the bulk, is S bulk semi-classical of S bulk semi-classical of minus A union minus B on the left and A union B on the right. Am I doing this right? Yeah. Oh, sorry. This is sorry. It's minus B A. So I should write this. So this slice is minus B, y equals to minus B, and this point is y equals to A. This point is y equals to minus A, and this line is y equals to B. And that's why these are the intervals that I'm considering. Okay, interval on the right and union of these two. So this is what I want to compute, a semi-classical entropy of union of these two intervals. Okay, now long before, when we were discussing entanglement entropies of 2D CFTs, what I told you is that entanglement entropy of 2D CFT can be computed by just computing endpoint functions, or correlators of twist operators. Okay, so let's start with this. So let's say I'm working at a particular time. Okay, so let's say that this point here is T comma B. Okay, and this point here is T comma minus A. This point here is T comma A, and this point here is T comma minus B. Okay, so let me say, let me just write it on the next slide, is that y0L equals to y0R is equal to T. That's what I'm considering. And the 4-point function I really have to compute is this. And again, the strategy is the same. I want to compute entanglement entropy of two intervals, right? These two intervals here. I want to compute entanglement entropy of two intervals. I will compute this in the I will compute this in the W coordinates and then transfer them to Y coordinates. Okay, and that's how I do it. So in the W coordinates, this is the computation I have to do. Okay, so in the W coordinates, I have, and right now the twist operators compute nth ring entropy, and then I have to analytically continue to n equals to 1. But I have to put in the W coordinate of minus b comma t. So W plus minus are functions of y plus minus. Okay, and the points, the 4 points, I just told you what the 4 points are. Maybe let me just, yeah, these are the 4 points. Okay, these are the 4 points, and I want to just plug them in here, and this is the only, probably the largest equation I'll ever write. I minus n, setting at omega 0, a comma t. So when I say omega 0 as a function of y0 comma y1, and omega 1 as a function of y0 comma y1, which can be derived from this function, and I had given these expressions earlier. Okay, the 4-point function that I have to write down is this, comma omega 1 a comma t. Okay, and then so these are plus and minus operators which are creating branch cuts, and let me just complete this expression. I minus n, w0, b comma t, w1, b comma t. Okay, this is the 4-point function I have to compute in the w coordinates, right? So I'm putting twist operators on in w's in the w coordinate by transforming these points from y coordinates. Okay, this is what I want to do. Now let's again look at yeah. So a is equal to a is a constant value in y0, right? I mean basically what is happening, this whole slice which I have constructed is at a constant time. Okay, all of them are at a constant times in Rindler coordinate. So basically I can draw a Rindler slices such that all of these points lie on the same Rindler time slice. So maybe if I can draw it here, I'll just draw it. Okay, so the Rindler time slices are like this. Okay, and all I'm saying is that the 4 points that we are considering just lie here. Okay, and as I've told you that it doesn't matter what is the slice, all that matters is where the endpoints, because entanglement entropy just depends on endpoints, in the sense that you could have 2 slices which go through the same endpoints, but they'll have the same entanglement entropy, because the entanglement entropy is really property of the causal wedge of that interval. So what I'm saying is this is a t equals to constant slice, or maybe y0 equals to constant, and this is y0r equals to constant. Okay, so let's do that. And then so what I wanted to say, and now let me go back to the point that I have made quite earlier, is that if you take any 2 points which are constants in yl and yr, so if you look at these 2 points, the computation that we did earlier is that both of these points are at the same time slice in the y coordinates, and they're at a constant y coordinate. Okay, generally when you just take y equals to constant in the left and in the right, and then you evolve it in time, this is generally what happens is the length between these 2 points in w coordinate just keeps on increasing. Okay, so this exponential growth always happens. Okay, the point I'm trying to make is that what I'm trying to do is I'm trying to compute entanglement entropy of the 2 intervals, and these 2 intervals are basically where the twist operators are inserted. So this is on the left interval, and this is on the right interval. Okay, but the distance between these 2, which is so the distance between these 2 here, distance between these 2 points in the w coordinates, so distance in w coordinates is increasing as e to the power t, where t is the point coordinate. Okay, basically this length goes as e to the power t. Okay, so now what is happening is we have 2, and also the distance between these 2 points, the interval on the left and then the interval on the right, that means this interval and this interval are just constant Rindler positions, right? And those so I can take a future 2 points, in the sense just shift these points to the future, where they'll become something like this and this and this and this. Okay, and then you'll have a slice in between them. basically some sort of entanglement wedge. Okay, the two slices I've drawn are basically are related by boost symmetry in the W coordinates, because there's a, you see the time translation in the Rindler coordinate is really boost in the W coordinates. Hence, the distance between the pairs in the W coordinates remains the same. Sorry, let me, maybe I should name, it's very hard to, okay. So let's call this point number 1, point number 2, point number 3, point number 4. What is happening is that 1 and 2 points remain at a fixed distance. 3 and 4 remain at a fixed distance, but when distance between them goes as e to the power t. Okay. So what is happening, and people who must have studied 4-point functions in 2D CFT, we know what is happening here is that these are OP limits of two other in a particular channel, depending on how you name these. And in this limit, cross ratios either go to 0 or 1. Okay. What basically happens is identity channel dominates and you get a factorization. So this 4-point function just factorizes into 2-point functions, a 2-point function on the left and 2-point function on the right. Now keep in mind, this only happens at late time. It doesn't happen at early times, because at early times this bridge is not that big. But what just happens is that at late times, point number 1 and 2 and 3 and 4 are relatively far away from each other than they are to each other. Okay. So in the factorization limit, the 4-point function that I had just written down is just a 2-point function. And now let me it's just a product of 2-point functions, which is basically so now I'm just writing as points 1 and 2, and whatever coordinate you want to put in, you have to do. So let's say these are W coordinates. So this is a W1 and this is a complex coordinate. So plus minus W2, and then so this is what it approximately becomes at late times, because the 4-point function factorizes into 2-point functions.
Shubham has a question.
Yes.
I mean, the factorization property has something to do with because this is a holographic system.
No. We see, the thing is, again, I'm just saying that we want the honest to goodness computation that we want to do is this. Is this quantity here, right? It's it's an entanglement entropy of 2 intervals in the bulk.
Right.
Okay.
Right.
Now I have already told you how to compute anything in the bulk.
Right.
The simplest to do is it in the W coordinates. You compute it there and you transform those answers to Y coordinates.
Right.
So in W coordinates, it's the 4-point function, because it's
Correct.
an entanglement entropy of union of 2 intervals. So this expression I have written is an expression in the W coordinates. Okay, this is a W coordinate expression. Right. Okay, and then all that happens is that because of the kind of parameters that we have chosen, this sort of factorization works out.
I mean, like you always have like this is the identity piece, and then like you have the conformal block contributions, right?
Yeah.
So what happened? They are suppressed.
They are suppressed by just time. I mean, the ratio of t or beta, something like that. So this is a different limit. Okay, so maybe I said the wrong name. This is a different limit than OP limit. So generally, higher block suppressions are in either 1/c or exponential in C.
Right. I mean,
so this is not that suppression. This is a different kind of suppression, which is this is suppression in time. It just, I think I might be wrong here, but the proper name is, I think, cluster decomposition in some sense.
Okay. Right? Clustered. I see. Okay. Fine. Yeah. Clustered. Yeah.
So that's what's happening here. The 2 points are just coming close to each other, and in time you can just write them as this product of 2 point functions. Okay. Now computing 2-point function is quite easy, because we know what the formula for 2-point function is. It's just the log of length upon length divided by epsilon. And we have already done such computations in our in part of this lecture. So what happens is that the extremization problem at late times just is an extremization problem of this quantity, of this factorized object. Okay. Before so in early times, what you really have to do is you have to compute this this quantity, which will give you Rene entropy. Okay. Then you have to analytically continue n to 1. That will give you entanglement entropy. Then that entanglement entropy, you have to plug it in this formula. And then you have to extremize over A. You have to extremize the generalized entropy over A. This is the procedure that you have to do. But now what I'm saying is that this highlighted green piece at late times just becomes a product of 2-point functions. So the Rene entropy part of the computation just becomes product of 2-point functions, and then we can analytically continue just this part. So from here I can go to the entanglement entropy of both of these pieces, and the product will also be the entanglement entropy of the which should have been computed from the 4-point function. I'm saying a lot of stuff, but please do keep on asking me. I'm just doing calculational trick to compute this highlighted thing here. So the highlighted thing is SF, a fine-grained semi-classical entanglement entropy of 2 intervals, and whatever I'm describing after that is just how to compute it. Okay, and I can't compute it exactly because it has to be computed by this complicated 4-point function. So the only way I can compute it is I can compute it at late times. Okay, so at late times, what really happens is that, so let me just write down the expression and then wait for questions. So S generalized A was supposed to be twice the value of dilaton for G Newton plus fine-grained semi-classical entropy of the interval minus B comma A on the left, union interval minus A comma B on the right. Okay. Now I'm just, by this factorization problem at late times, okay, which is basically saying that T is much greater than beta, what really happens that this formula just becomes this. Plus twice the semi-classical entropy of, you can choose any of the interval, either minus B to A on the left or minus A to B on the right. Okay, is this clear? Okay, so let me just wait here and then maybe I'll just give you more details of how to do this computation. But this is what happens at late times. I'm really supposed to do this computation, but that piece just boils down to this piece at late times. And after this, I'm going to do extremization. After this, I'm going to say, I'm going to extremize over A.
Shubham has a question.
Yes.
So if I understood it correctly, like at early times, you have the null set to be the dominating piece in the correction to Bekenstein-Hawking piece, right? And
yeah.
then
So the thing is the null piece. So this is the null entropy, right?
And
it
that
doesn't
is
have
early.
the area piece at all. It just has
right. I'm saying that this S L union R, you have written minimum of this thing and late time also. So the early time is dominated by S gen phi, and then after that you have the whatever you are now trying to compute, right?
Yes.
And what is setting this early time scale and late time scale? Because I can also think of a time in between when, minimum becomes S gen A extremal, but you still don't have cluster decomposition.
Oh, so the
is it like, am I
yeah, then you really have to do the 4-point function computation.
So like it's not a priori clear that this will like the time scale for like when A extremal, S gen A extremal becomes the minimum piece and the cluster
yeah, it's not clear, but let me tell you what is the time scale at which the exchange between, so the page time, what is the page time? The page time where the actual exchange should happen between S generalized null and S generalized A is this. So the page time is really beta into S Bekenstein-Hawking divided by C. This is what happens. Okay.
And this is the time when you have the switch over from the null set to the AX.
Yes, exactly.
Right.
But the formula that we are writing down is only valid in this region. So probably it's valid much later than page time.
Right. So
that's true.
Yeah, so I see. But you are anyways interested in the late time radiation, or
yeah. So all I'm interested in showing, so the exact what exactly happens at the transition point is much more subtle. Okay. But all I want to convince you that early time it's linearly growing, and at late times you do get a constant answer. And I also want to show you that constant answer is really the twice of Bekenstein.
Okay, I understand. Okay, thank you.
Yeah, so now this is the computation I really want to do. And I so first of all, for any possible a, whatever a doesn't have to be extremal. So right now I'm not writing a as a extremal, I'm just writing a as a. So it's a contender surface still, but you can take any contender surface, and for any contender surface this cluster decomposition kind of thing will happen, and this formula will be approximately valid at late times. Okay, but now I'm just doing extremization problem at late times. Okay, so first of all, let me just exactly write down what this formula is.
Adwait?
Yes.
So you have 4 minutes left on your regular time. How much time do you think you should need extra? 15 minutes should do the trick.
Yeah, in 15 minutes I should be able to make the point. Yes.
Yeah, so let's do one thing. Let's let Adwait finish, wrap it up. Then we can take all the questions together at the end.
Yeah. Thanks. Okay, so yeah, anyway, so fine. So okay, if you do maybe let me not waste time here. I'll put my written notes on the Slack, and you can look at the extremization problem, or it's available in Maldaceno's Islands Outside Black Holes paper. Let me just write down the final result. That final so if you extremize, so basically the extremization problem over S gen of A becomes this. So it's a very, very complicated looking expression. Nonetheless, let me write it. Equals to 12 pi r by c beta into 1 upon sin hyperbolic 2 pi a. So this is the solution to this equation is the a extremal. Okay, the solution to this equation is a extremal, but the point is it's very hard to solve this solution. So now we go back to this old trick where I had said 1 over g Newton is much greater than c, and in our GT context the 1 over g Newton was phi r by beta. Okay, so hence the limit I'm going to take is phi r by beta c is much greater than 1. This is the limit. If I use this limit, what I get is a extremal is approximately equal to b. So b was the a small piece of bath that we had on the exterior, plus beta by 2 pi log of 24 pi phi r by c beta. Okay, so this is what you get. So there is a non-trivial, first of all, there is a non-trivial extremal point. Hence, not all of the, so what does this really mean? What does this really means is not all of the interior is really dual to your field theory, right? Because what did we say? The entanglement wedge reconstruction proposal says that if you take a subregion and if you consider entanglement wedge of that subregion, everything in that entanglement wedge can be reconstructed from that subregion. Okay. In our problem, we are not considering subregion. We are considering all of the field theory, all of the CFT1. Okay. So if I am considering all of the CFT1, the naive guess would be all of the CFT1 reconstructs all of the bulk. So the entanglement wedge of the two dots should definitely be all of the bulk. But that's not what's happening, right? Because there is a non-trivial extremal surface. What it says is that this particular piece called island does not lie in the entanglement wedge of the CFT1. Okay, so that information, the information about how to construct an operator which is sitting in the which is sitting in the island is not there in the CFT1, the 2 copies of CFT1. Then where is it? Okay, and the point is it's in the radiation. It's in the BL and BR system. Okay, so let me and then if you you can just plug this back in the formula that I had given before of S generalized A, and you'll see that S generalized A will be approximately equal to the twice of S black hole, S coarse black hole. So what is that? Yeah, it's basically just this object. It's the dilaton, the extremal value of the dilaton plus 2 pi phi r pi beta, okay, which is equal to twice of S black hole. Coarse grain entropy of the black hole, which is also the value of the dilaton at its horizon. Okay, so area is really the horizon, so it's just a coarse grain. So now what I have shown is that if you compute, so what did we really do? Again, what we really computed and fine-grained entanglement entropy of the of these 2 intervals. So we even holographically, I was computing fine-grained entropy of the dots. Okay, so in the dual picture, I was computing fine-grained entropy of the black hole. Okay, and what we have seen is black hole solves the information paradox in the sense if you use this Ruta-Kanagi prescription, and if you choose that after a point you have to change the extremal surface, after a point you have to go from the trivial surface to the non-trivial surface, you see that it reproduces page curve. But then you have to think about what it really means for the bath. Now let me just quickly sketch what it means for the bath. Okay, what was the bath calculation that we did earlier? And the bath calculation was this. Okay, we said that S fine grained, and this is some minus B and this is B. So we computed S fine grained earlier of minus infinity to minus B on the left, union B to infinity on the right. Okay, we did this computation, and we did this computation with using, we did not use holography, by the way, we did not use holography, but we saw that this thing naively, okay, naive in the sense what we were doing in the corresponding bulk calculation is we were always computing S generalized of the nulls of set. Okay, and we saw that this always increases. Okay, so but this object always has to be by unitarity, because there is a pure set across all of these 2 systems. By unitarity, this also has to be equal to minus B comma 0 on the left, union B 0 comma B on the right. Okay, and this we saw is basically minimum of was minimum of S generalized phi comma S generalized A. Okay, now how is it that these 2 quantities are equal, but these two quantities are not? Okay, the problem here is very simple, that if you remember the computation, this was this thing was computed by QRT prescription, and this thing was not computed by QRT prescription. Okay, it was just a naive guess. What we did was, if I let me remind you of the computation, what we really did was we said that I want to compute entanglement entropy of the BL and BR, and I know that BL and BR entanglement entropy of the BL and BR will be equal to entanglement entropy of the LR, and then we just computed entanglement entropy of the LR forever. Okay, so what does the entanglement entropy of, so let me try to write down the correct formula for this, and then we can discuss what happens. So the fact that the quantum Ruta-Kanagi surface has a first order phase transition for the black hole system, in the sense for this system, holographically implies that you the correct formula for the radiation, which Hawking should have used, was this. He should have, so this is really F of the radiation. Okay, now what it means to be radiation is we can discuss about that, but this is really the this is what it should be, and that is yeah. So let me write down the general formula, and then we can, this should be equal to minimum of the extremum of area of the boundary of the island. Okay, now this area is what we called as dilaton in our example, plus fine-grained entropy of BL union BR union island. Okay, now why? Because if I was just computing fine, maybe I should put another diagram. So let's just look at the bulk, and I'll really stop here. Let's just look at the bulk, and we had these slices. So there was a slice from here to here. There was a extremal surface, which was here, extremal surface here, and then there was this slice. Okay, and then there was an island in between. Island. Okay, so and then we had, so at the boundaries of the at the extremal surfaces, which are also the boundaries of the island, we take the area pieces. Okay, and let me name these things. This was BL, this was sigma chi L, this was chi L, this was chi R, this was sigma chi R, and so maybe I should put some dots here just to divide the space time. And this slice here is BR. Okay, so what we showed was the fine-grained entropy of the black hole system, meaning the fine-grained entropy of, okay, so the fine-grained entropy of the black hole system, which is equivalent to, in the 1D point of view, fine-grained entropy of minus b comma 0 on the left, union 0 comma b on the right, is equal to twice of, so let's only write down at late times. It is equal to phi a by phi a by 4g Newton, right? And plus the bulk term S fine, which is also should be computed in the bulk of sigma chi L union sigma chi R. Okay, then what does really, what does really remain, in the sense that, so if I want to write down SF of the radiation, so I'm writing it white because I want to compute, I want to understand in the bulk, that will be S fine grain of minus infinity comma minus b on the left, union b comma infinity on the right. So this by this formula is supposed to be BL union BR union I, and the area of the boundaries of islands. Okay, so areas of the boundaries of the island are still the same. They still give you 2 phi a upon 4g Newton plus a fine-grained entropy of BL union BR union the island. Okay, so the only thing that was missing earlier was the when we did the computation of fine-grained entropy of the radiation in the bulk, we did not have this piece. We did not have this piece here, and we did not have the island. Okay, so what we did was we just computed SF of BL union BR, and we said that that is equal to, in the bulk is equal to, so as very early on, I had said that this equation is going to be the wrong equation. Okay, in the bulk, this is not exactly true. So okay, that's the point, and maybe I'll just stop here and take questions. I'm really sorry to not complete the course, but I think at least I must have done a job of getting you excited about the topic.
Okay, I think before we take questions, we should thank Adwait not only for this lecture, but for the entire 6 lecture series. So let's have some questions. Shubham, go ahead.
I got a bit confused in the last part. Like, can you just go to just a few slides before this? Yeah. Right. I mean, yeah. How did you? Where did the last S radiation come from? Can you just explain it a bit more again?
Yeah. So in the 1D system, just think about in the 1D system. As I said, 1D system is the most clear thing.
Yeah.
Right?
Yeah.
So in the 1D system, what is S radiation? So in the 1D system, S radiation is really the fine-grained entropy of the interval minus infinity to B, right? So this is the computation that you are really supposed to do. This is what I would call S radiation, the fine-grained entropy of the radiation.
All right.
Right? Now, I just want to see what it becomes holographically in the bulk. And if I just follow my nose, the formula that I should get, that I get holographically from the bulk is this.
Yeah, this like, I mean, I like that. I mean, I can't see it immediately. Like, maybe I should.
Yeah. No. I think I should have done a better job of explaining this. But
like, I understood your 4-point function calculation. So can you just, like, I mean, from the 4-point function calculation, can you just say what?
Yeah. So yeah, let's go to the 4-point function computation. Yeah. So the entropy of the black hole is computed by this computation, right?
Yes.
You have a dilaton here.
Yeah.
Okay. So you compute area pieces from here.
Yes.
And then you compute fine-grained entropies of these pieces. So S fine, and all of this is being done in the bulk. S fine of sigma chi L and sigma chi L. Okay.
Yeah.
So
that is the nice 4-point function calculation that you.
Exactly. Yeah. Now, this is in the 1D system. This is the computation of this interval. These two intervals, right? It's minus B to 0 and B, and 0 to B. Is this clear?
Yes.
This is a 1D point of view. The computation I want to do I wanted to do this computation holographically, and the way I do it is just do it across. I compute the fine-grained entropy and I add it. I areas to it. This is what quantum root Takanagi tells me.
Yes.
Okay. Then what is the entanglement entropy of the remaining region? In the sense that if I want to compute entanglement entropy of this region,
right,
minus infinity to B, and here also I want to compute it of minus B and B to infinity. Okay. Now just look at the surface. Okay, look at this thing. If I assume that there is a pure state in the bulk. Okay, if I assume there is a pure state in the bulk, there are 3 remaining parts. There is the BL part, there is the island part, and then there is a BR part, right? So there is an island here. Hence, what I should be really doing is for the island computation, I should take so this is just a prescription for now, and I really wanted to tell you about replica wormholes where you can derive this. But the naive prescription would be that if you want to compute entanglement entropy of the complement in the 1D system holographically, you should take area pieces, because the original prescription also contained area pieces, and then just contain fine-grained entropy of BL union BR union I, because in the bulk this statement is true, that fine-grained entropy of sigma chi L union sigma chi R, okay, will be equal to fine-grained entropy of BL union PR union I.
Right.
Now the only things missing are the area pieces. Okay. So you just add area pieces on both sides. So on one side they get added as area pieces of the extremal surface. On the other side they get added as area pieces of the island.
So they are the same. You're saying, like, I mean,
they're really same, but they're being added on both sides. So this is what, So this pieces which are there here are the same pieces, are being counted in the both. Are being counted in both computations here, and for the complement or not.
And like maybe a night question. And can you see, like, can you show me, like, I mean, how the area piece of the island is exactly? Is it trivial to see that it's the same as the?
So it just comes from this, that if I have okay, how do I say it? If I have a complete system, let's say a holographic system, and if I take a sub-region A, and if I compute quantum extremal surface for that, and the complement to that is A prime, the quantum extremal surface for A prime is also that.
Right.
Okay. So the quantum extremal surface for this system holographically came out to be some extremal A.
Right.
And by just complementarity, the quantum extremal surface of this system is also the same surface. But the only novel thing here is that your bath is not holographic. Right? The only dot was holographic. But now this formula which I have written down here, the second formula, the island formula, is really you're applying holographic ideas to systems which are not really holographic. In the sense, you have somehow found out how holography works in the limits where it's not easy to see holography.
Right. I see. I mean, truly, this the way to understand this is that truly this S fine-grained, this relation that you have written in the last slide, it's the true statement. I mean, this is
the right way to understand is this is the true statement, really. S fine-grained in the 1D system. 1D system is the true system, because that is what we understand all the time. So this is the true system. This is the true thing, that S fine-grained of this has to be equal to S fine-grained of minus infinity to minus B, left union B to infinity. Okay. This is a true statement. Now the point is, the right hand side of this equation cannot be computed holographically, or at least we did not know how to compute it holographically.
I understand it.
The left hand side, I knew how to compute it holographically, and I showed you how to compute it holographically. Right? But the left hand side clearly made sense. It gave me the right unitary things. So how should I modify the holographic interpretation of the right hand side formula? And that modified holographic interpretation of the right hand side formula is this. Or more generally, this.
I now understand.
Nice. Okay.
Rohan had his hand raised. Rohan.
Yeah. So basically, the radiation entropy keeps on increasing with the island, is it?
Yeah. So let me put this thing here, and let me add this diagram, which is more easier to. Yeah. This is what you have. So what the A figure is the figure where you're not considering any island. And what is happening is, you see, I was talking about these pairs being either captured by a BL or BR or not. So initially there is no island. Hence, you see the blue and green pairs are captured by external things. But at the point when you start including island, what happens is partners of these are also being computed. Are being included in the island, and hence entropy starts decreasing again, or it just becomes constant at some point.
Okay.
So basically what we are saying is that the interior is really the island part. So how in the words of entanglement with reconstruction, what do we say? So whenever we are saying, so if I want to create some excitation sitting here. Okay. If I want to create some excitation sitting here, yeah, if I want to create some excitation sitting here, or if I want to find, if I want to, if I want to construct an operator which is sitting here, I can really construct it from here. And that can only happen at late times. It can't happen in early times. Why? Because entanglement wedge of the radiation island is contained in the entanglement wedge of the radiation. But at early times, it's not there. So early times, if you throw in something, that is still with the black hole. But when the island appears, that's exactly when the information has escaped. In the sense, all the information that is supposedly in the island is also in the, can be reconstructed from the radiation again.
Okay.
So at late times, once you start once you include this island in the middle, the ever-growing entropy stops increasing. It just becomes constant, at least in the eternal black hole case.
Okay. Okay.
Tushar, go ahead.
Right. So it looks like this island region always extends just outside the horizon. Is there a reason why this is so? I mean, even
so the fact, the only non-trivial thing that you should take away from this is that there is a non-trivial point. So it could be either inside the horizon, it could be either outside the horizon. So for the eternal black hole case, it's outside the horizons. And for evaporating black hole case, this mostly lies inside the horizon.
Okay. And okay, so just to make sure I understand this island, what happens is that if you had only included the bath entanglement wedges, then the entropy of the radiation would keep on growing, but this island starts to include the entangled pairs, and which purifies it, and hence it sort of saturates, as you were explaining. That's the main point, right?
Yeah. So as I was saying here, so the entanglement wedge of, so in this sphere diagram, which I'm drawing here in the, this diagram, the entanglement wedge of A is this.
Yeah.
And the entanglement wedge of the complement is the rest of the region. Is this. Okay. So entanglement wedge always come in. So A union A prime is the full boundary. Then sigma A, which is the entanglement wedge of A, union sigma A prime, should give you the full bulk. Okay. Hence, once we are saying that the entanglement wedge of the boundary system, so in this diagram here, the boundary system is somewhere here. So what you would say that the entanglement wedge of the boundary system of these two dots are these sigma chi L and sigma chi R surfaces. But then what is the entanglement wedge of BLBR system? So the entanglement wedge of BLBR system is really island, because it has to be the complement. Right? Everything in the bulk has to be reconstructed, everything that is non-holographic. So what is non-holographic? What is the boundary? Boundary systems are BLBR and the dots.
Yes.
So if dots are what are reconstructing sigma chi L and sigma chi R, then islands are being reconstructed by BL and BR.
Okay, Akhil has a question, and his is the last question that we will take on record. So Akhil, go ahead.
So what we did, I'm understanding it as like I connected some 1D quantum mechanical system to a bath, and then these things equilibrate. Is that right? Like you wait for some time, and then radiation it decays, sends energy. I mean, maybe it's in a maybe we match the ingoing and outgoing energy, and it doesn't really leak out. But we somehow let the entanglement entropies evolve and so on.
Yeah.
And then you at some point you realize, after this island prescription time kicks in, you realize that some degrees of freedom of the quantum mechanical system should be identified with the degrees of freedom of the bath. Is that right?
Yeah. So let me maybe say another a few things about this. So there's something that people had asked me before, and maybe let me just say this before. So what is the meaning of the so when you have two dots, okay, the dual of that is this eternal black hole space-time. So I'm just drawing t equals to 0 slice, okay, and I'm taking the state to be t of d, and this is t equals to 0 slice of the eternal black hole. This would be equivalent to writing S CFT on the CFT side, and that would be equivalent to writing the action root gr plus lambda on the bulk side. Okay. Now, what I really want is I want this I want to put some scalar fields. So first of all, this first section which I have drawn here is just gravity. So this is the ADS CFT correspondence for gravity. Now what I want to do is I want gravity, but I want fields also. Okay, I want fields on it. So what I really have to do is, so let me just draw the three things. What I really have to do is I have to deform the CFT with a source with a single trace operator. Okay, what does that do on the left hand side? On the holographic dual, the manifold is whatever it is, but now there are some fields on this manifold. Okay, there are some fields on this manifold, some scalar field. Okay, and these points are the end points of the manifold. Eternal black hole, we are discussing the usual holography. Now let's go one point further. What did we do in the bulk? We had a bulk manifold which ended somewhere here, and we had some scalar fields on this. Okay. Now we also extended this bulk manifold outside by attaching some BL and BR. Okay. So here, what does this mean? So the Lagrangian of the gravity in the second part, when we just added the field, was, and let me call the region in between as some maybe, I don't know. So let's first write. Let me just write this. This is what the Lagrangian looks like. Okay, and this is only over the bulk manifold. Okay. But now I have added the extra pieces of BL and BR, and I also want this scalar field to leak outside. What does that mean? That means that, but I don't want gravity to leak out. So my Lagrangian for the gravity remains only in the bulk. Okay, but I have two pieces for my scalar field. There is a bulk piece, and then also there is a piece which just extends over BL union BR, and that is also a scalar field. Okay, and all I have to do is I have on this boundary points, I have to match the field. Okay, what does that do here? That just says that I have S conformal field theory, which is connected to J. So now let me write it as phi. Okay, and yeah, let me write it as phi of X, O of X. Okay, and then this piece is non-holographic. So I just add this piece here. BL union BR of del phi square on. So now this, so here what was happening, there were two dots, but two dots were defined by this deform theory. Now I have a dot, but now I am attaching these two manifolds to the dot, and on these two manifolds I'm putting this theory. Okay, so this is how you should understand the ADS CFT of this hybrid model. Okay, so when you have gravity, there is nothing. There is a conformal field theory Lagrangian on one side and root GR on the other side. When you add fields, you deform by single trace operator, and there you add fields on the bulk. Now you add an extra manifold to both the theories. You add it to the holographic 1D CFT also, and you holograph to the bulk also. And then on the bulk, what are we doing? We are just saying that this Lagrangian sitting here is exactly equivalent to the Lagrangian sitting here. Hence, the remaining piece is constant. Remaining piece is what it is, but I'm just interchangeably using these two Lagrangians.
Yeah. So can I just complete my question?
Yeah.
Yeah. So I had this doubt about the picture slide 60 you have, like where you showed that you can do something in the reservoir, which is 2D, a 2D field theory, and really excite gravitons in the 2D bulk. Right?
Not gravitons, just the field theory excitation, just the CFT excitations.
You can't excite okay.
I mean, we did not do analysis for gravitons. We should have, if we did the analysis for gravitons, then then the island will be slightly modified, and then.
But it shouldn't be really possible, right? But because I usually hear the statement like you can't really wrap up fields and make gravitons. But then someone would be like, oh, okay, how did that happen in ADS CFT? Then you always like, oh, look, you really made gravitons in one higher dimension. So no Weinberg-Witten and so on. But now you're saying 2D field theory, you can excite gravitons in 2D gravity. Am I understanding something wrong? Or?
No, are you just saying that there are no gravitons in 2D field theory? That's why?
No, I'm getting confused this way. okay, maybe I'm not understanding any of these statements, but I usually hear Weinberg-Witten's theorem says you can't really wrap up field degrees and make a 2D, make a graviton. Maybe there's a very loose characterization of the statement, but then someone would be like, okay, in ADS-CFT, you really wrap up a field theory and make gravitons in the bulk. But then the reply would be
Weinberg-Witten's theorem says that any consistent quantum field theory which is Lorentz symmetric cannot have a particle which is spin 2 or spin 1. I don't know, greater than spin 1 or something like that, and hence a consistent Lorentz invariant quantum field theory cannot have a graviton.
Right. So I just rephrase it as like wrap up field degrees and make it look like 2D, spin 2 particle. Right?
Yeah, but
no, there is a Weinberg-Witten for the spin 2 as well. If you have a local conserved stress tensor, then you can have Atmos spin 2 and not higher than that.
I see.
So I usually hear the statement ADS-CFT works because your gravitational system is living in a one higher dimension. When you say bulk gravitons can be dual to field degrees of freedom, it really is consistent with Weinberg-Witten only because it's in one higher dimension.
Yeah, maybe there is a subtlety to this all of this constructions when you're considering fields which have gauge symmetries in them. But if you can, I mean, yeah, in 2D gravity, the gauge symmetry of the gravitons is just SL2R. So it's quite trivial. So maybe you might be able to just do this in 2D gravity. Because these gravitons are just boundary gravitons and they just have some SL2R degree of freedom, which is very small group than a complete different.
Oh, you're saying even the gravitons in the bulk are really boundary degrees?
There is no graviton in the bulk. This is the point. There's no propagating graviton.
No, I mean, in the 2D, yes, but I guess you would use the ideal prescription.
Sorry, just to interrupt. It's already past 1, and I feel that this discussion is sort of going into a tangential direction. So maybe we can pause the recording here, and people can continue these discussions more informally. But before we pause, let us please thank Adwait again for this wonderful set of lectures. Please unmute yourselves and clap. Okay, welcome to the post-lunch session of the final day of ST4. Parthiv is going to give his final lecture as well as ST4 2020's final lecture. So over to you, Parthiv.
Yeah. Okay. Just to refresh what we were doing last day, we were actually setting up this numerical methods or numerical algorithms for Bootstrap. So we had reached up to the point where we had told, I reached up to the point where I represented the unitarity condition in a form which will be implemented in a computer via in terms of what is known as a semi-definite programming. But so let me go on a little bit and try to take an example, an explicit example for what kind of problem that we're trying to do. So before that, so this is actually taken from this paper. That I just a second. So this 17.806.765. Mm-hmm. 765. So this is taken from this paper. So basically, it's a simple. So the kind of always we are interested. I mean, the kind of problem that this numerical bootstrap deals with is always some kind of optimization problem. I mean, what? Optimization, and therefore people actually find bounds. people actually find bounds. So a problem that they considered was this, that they were considering a scattering amplitude with a simple pole, that means a single bound state, of mass mb. So essentially what they are trying to see is a kind of cubic coupling kind of scenario. So they're considering that m, but something like that. So this is and the coupling strength is, of course, the coupling strength is given by this this g square introduced. So if suppose so this kind of cubic coupling, so this is just one problem. I mean, this is just one problem from that paper, but that will serve as an example for the kind of stuff that we're trying to do. So this is a problem of cubic coupling kind of structure, cubic coupling kind of stuff. And just to mention here that if you would have considered, like if you could have taken that mb equal to m not equal to m, then this would have implied already that there is no cubic coupling which is of the form this. So if the mb is not equal to m, if you consider that assumption, then this kind of cubic coupling would not will be excluded a priori by assumption. So the idea here is that, so given an m, and we will consider a range of value of mb between 0 and 4, and we will optimize or try to find out over this spectrum the maximum value of mod g, but more importantly, where does this maximum happens? So it is this kind of problems one usually looks into when one does this kind of numerical bootstrap exploration.
Sorry, here when you say 0 to 4, the range of MB, do you set the value of M to 1 or the physical mass to 1?
Yeah, right. Yeah, sorry.
And then in that case, the external masses that you have written down, MM. So what are those? So those will be what, 1 or the same?
Yeah, those will be 1.
Okay.
Parthiv, will it not be 2m less than 2, or because you are not squaring it?
Oh yes, yeah. So let me just right. So it's b square. So this is 1. This is 1. So yes. So this kind of problem. So this is just one simplest problem in that paper, anyways. But the point I'm trying to emphasize is this: that we are always looking some kind of optimization problem, and people actually obtain bounds on this kind of parameters like g square and other kind of amplitudes by this kind of numerical bootstrap investigations. Okay, so let me go to the next slide. Now, so let's be so what kind of optimization problem? And this optimization problem actually is of a special kind, which is known as polynomial matrix program, or PMP. So this is a special kind of optimization. So let me try to define what is a PMP. So one considers a set of symmetric polynomial matrix of this structure yeah, okay. So this kind of structure where N and capital J, where each element, that means this PNJ11X is a polynomial in X. Now, with this structure, so let me go to the next slide. Now the problem is there's a vector given to maximize over Rn such that for all x equal to 0 and capital J. So what does this mean? That one wants to usually try to maximize this kind of a linear combination, like b naught plus b dot y. So b naught is some constant. So b naught here is some real number. B naught is here some real number, and one wants to maximize that quantity b naught plus b this b vector and y vector. B vector was given such that this kind of a positive semi-definite condition. So this is the constraint. So let me highlight the constraint. Now note that this is not a single constraint. This is actually multiple constraints. Like there are capital J constraints. So there are multiple such semi-definiteness constraints. So the right-hand side is actually, sorry, left-hand side is actually a matrix. So what this requires is that, so formally the problem says that when find out a y belonging to Rn such that which maximizes this quantity b naught plus b dot y, but also at the same time satisfying this semi-definite constraint, these semi-definite constraints. So one will look for such y numerically, scan the Rn space for such an y to find out the optimal solution. Now let's try to see that for our problem, what is this various vector sum. So for, let's now this problem for work is at hand. So let me go back to so first thing is of course you have to find out the y, that we have to identify the y. So this y is in our case the eta vector. So let me go back to this slide number 75. So this eta vector is basically the parameter vector. So it's a g square alpha. So the entire parameter vector. But we are interested in maximizing only g square. So we will also have to specify, and that information that we are just focusing on one parameter out of this entire number of eta vector for the optimization procedure. That information will be provided by that, rather I would say that constraint will be provided by this b vector, which will be suitably chosen. So for our problem, we will choose b vector to be something like that it will be the one at the position corresponding to g square. So let me just write down here for completeness. This is g square, alpha 1, 0, 0, and so on. And all other similarly. So note that clearly. So you can just throw in I mean, b dot eta is equal to simply 3g square. And for this problem, b naught is chosen to be 0. Okay, so this is what we are going to one wants to optimize. But now we have to understand what are this various elements of this constraint. That is, what is the connection of this MJ matrices and whatever we have constructed. So let me go to the next slide. So what we have constructed, the matrix for us, the entirety constraint was manifested as a matrix being semi-definite, where M was like this. And what was, just to recall, R was and Ri and FLS was Yes. Where TSX was constructed by the way that, remember that usual TSX was by separating out. So this vector TSX had only only the SX dependent factor, only the X and ST dependent factor. Okay, from this M, we are going to write down the M in this fashion. So we are going to write down, so we wanted that this thing is positive semi-definite. So we are going to write down this M as this fashion. So if I now define and where Ri is simply, so Ri will be simply real of FLI. Then this constraint, if I writing this, then this constraint can be cast into the form equal to some, depending on the I, and these are explicitly, these are polynomials in row quite explicitly. So these matrices are polynomial in row variable, which are functions of S, remember. But numerically, when we are going to implement, we are going to choose value in row. But this still does not explain one index, that is this J index. So far we have taken care of the I index, and see, I runs from 1 to N, so 1 to capital N, where capital N is determined after all the variable elimination that we did, that we discussed yesterday. So I is determined after that. So it's essentially dependent on that N max that we introduced yesterday.
Parthiv?
Yeah.
So this eta, are they same as the y's that you introduced earlier? I mean,
yes.
Is there any relation between the constraint relation that you wrote down a few slides back in terms of y and b?
Yes. So basically, I am trying to. So this was the expression for the general problem, and I'm trying to now cast my problem, like the actual S-matrix bootstrap problem, into this general form, so that I'm identifying why. So for example, so this is the general mathematical statement, and for my problem, y is eta, and b is this special vector that I just wrote here.
Okay.
So that's how I'm just setting up the problem. And similarly, I'm just defining the MJs. Okay. So as I told, so there's this. So what we have to understand also this small j index, because that small j index had to make sense. That means what is the number? So what are the constraints? So it's clearly I emphasized here that it is not a single constraint, but it's a multiple constraints depending on how many j's are there. So the way these j's are obtained, so how many constraints are there? So we have to make sense of. So let me just write it down here. J index. So the way this is done, I mean, so what is this J? It's in this sense. Of course, you choose. We are told that you choose L is chosen to be less than some cutoff L max, and you also have to choose S values. So chosen from some grid of values. From some grid of values. So now I have a matrix rho, but then rho is also function of S. We'll see how these are chosen. So there is one such matrix for each pair LS chosen as above. So what does it really mean? So if I just try to write the pictorially represent. So suppose you are choosing. So it's a double grid kind of stuff. You are choosing certain value of L. Let's say up to if you're identical, so it's like 0, 2, 4, 6, and so on and so forth. Similarly, you are choosing some S value according to some distribution or some kind of function, and then you have, let's say, so at each of these crosses, so what I mean to say that at each of these crosses you have one has one constraint of semi-definiteness. So each of these crosses, at each of these crosses, you have one such semi-definiteness constraint. So suppose if I would have chosen this way, clearly there are 15 constraints you have to take care of. You have to go through the 15 constraints to find out, to solve the ultimate problem. So let me once again tell algorithmically what we did. So let me just recap. So the problem is what they call is a polynomial matrix problem. So let me just go back to slide 79. So the polynomial matrix problem is this, that given a vector B, one wants to maximize B naught plus P dot Y essentially over Y, which is also belongs to that some kind of Euclidean space, such that a number of semi-definiteness constraint is actually satisfied. Now, the case that we were considering, that we wanted to maximize this G square with respect to a certain MB value. Now, remember the MB value here has entered this MB value has entered this MJ matrices. There, we can cast the same problem into this polynomial matrix problem by making this identification. So Y is basically eta vector for us. For the problem at hand, that because we want to maximize, extremize this, maximize this G square, we have chosen beta equal to 1, 1, 1, 0, and all other entries are 0. And the matrix MJs are constructed out of this capital M matrix that we introduced. So like that one that I've written in the slide number 80, because this semi-definite, because unitarity was expressed as semi-definiteness of this matrix, and we constructed those MJ matrices that entered the polynomial matrix problem by the prescription, so that I defined in this slide 81, where each M0 J or Mij that entered the polynomial matrix problems are defined in terms of this, and then I have an exactly this unitarity constraint ultimately becomes a statement of polynomial matrix problem, and each the index J, that is how many number of constraints we have there. We have the same number of constraints, each for one L and one value of S, which is so you can think of like there's a double grid of L and S values, and each of the grid point you have one value of MJ. So each of the grid points you have one constraint. So at each of these grid point, you have to check this constraint, whether this constraint holds. And so these constraint holding, so computationally I'm told that this constraint holding and the extremization, they actually run parallel. So it's I must point out that it's a heavily computationally taxing program that is running. Now, how this is actually implemented in computer is via what is known as a semi-definite program, and that was something for Bootstrap. It was developed by David Simmons-Duffin. So let me write it down. CFT Bootstrap. It was developed originally for CFT Bootstrap, and all the most strongest results, numerical results of CFT Bootstrap are obtained by this SDPB. And SDPB actually numerically implements this polynomial matrix program to find these bounds. Okay, so the kind of results. Just to point out some technicalities, that SDPB is mostly C++, just to point out. But incorporates also mathematical codes. Yeah, and I must point out that this is STPB is heavily computationally taxing program. Taxing program in the sense that so for example in Peronis's paper Nmax was chosen to be 20, and for this kind the problem that was chosen I was just telling Nmax was also chosen to be 20, and for this kind of configuration they used around a around like so they use this whole to run this whole around 2400 CPU cores kind of system. So essentially you have to put this program into cluster to run this thing very strong. So yeah, it's a computationally heavily taxing program, and that so for example the state-of-the-art stuff that is done, state-of-the-art SDPB that is used in the case of CFT Bootstrap, people there use systems with 65,000 CPU, CPU core clusters, and often distributed in 2 or 3 supercomputers in different sections. Just to mention that our guys, so I did not do any in our recent work. We also used this. So I did not do any coding, but people who did them, they did it in a very restricted setup, like 50 cores. Somehow they pulled off. Okay, so one thing, of course, this is still missing the fact that how do we choose the grid? Of course, Lmax, the choosing the L is straightforward because of the 0, 2, 4. And so on and so forth. But how S is chosen? So for their work, they chose S in a specific manner. So let me just tell. So they chose S by, so they chose the row M, a grid of, so they chose a grid of row M by so this kind of, so it's almost, so they actually chose row to lie on, so they chose row to be almost uniform from, they chose M to be almost uniform from that boundary of that disk in the disk. And of course, the corresponding SM is just given by rho SM equal to rho M. And the precision in their paper they used, you have to use pretty strong precision, otherwise it will just give wrong things. So they use the precision of around 1,000 decimal points, because the numbers that enter into this whole program, that get input this whole program, that means this FLs that I introduced, these numbers when you actually calculate, they are very small. They are almost always of the order like 10 to the power minus 24 or so. So because they are very small, so you have to have very strong precision, otherwise things will be problematic. So let me just, so for computationally, how this thing is done is that there is 2 parts. So SDPB runs on cluster, on of course cluster, and input of SDPB are that what they call the objective vector, and these matrices. On the other hand, these vectors, like so for example, these eta and mji, these quantities are calculated in Mathematica interface. So what happens is that you calculate these things in Mathematica, and then you create what is called you create an XML file out of which, and the SDBP actually takes an XML file as an input, and that's why the precision is, you have to, so of course so even on the Mathematica you have to give high precision, otherwise Mathematica will just give 0 because they are extremely low, small in magnitude. The magnitude of this quantity is extremely small, so they will give you just 0 elements. The whole computation procedure happens like this way. So first, of course, you calculate these quantities in the specific values of the grids, and the grid is defined. So the grid they used is this kind of distribution, and then after obtaining the values, you just give this to the SDBP input of these values to get the code running, and the optimization comes out of that SDBP. Of course, it may seem that this grid choosing is somewhat arbitrary. I mean, they have not explained why they have chosen this kind of grid stuff. They just mentioned. I mean, Bhaya correspondence have just mentioned that kind of grid choosing. So yeah, these points are actually subject to experiments. One can try to see that whether choosing another kinds of grid will result into something else or not. Okay, so this was the computational setup. If there's a question, I can take it. Okay, if not, let me just, because there are many problems which are done through this stuff. So then let me just mention some of the result of those problems, just to be on the first page, but I will not describe the entire result, what kind of result that was actually.
Parthiv?
Yeah.
Yeah, just a naive question. I mean, why are these eta and aims calculated using Mathematica?
Oh, I don't know. I mean, okay. So I think this. Okay, yeah. So I think this eta in this. Well, eta is not calculated. Eta is just you give this, but the actual calculation happens in M, and M involves this integrals with respect to this Legendre polynomial. So I guess whenever there's that kind of special integral kind of stuff happens, they calculate this using Mathematica. I mean, I do not know.
So there is some semi-analytical thing that you need to do. That's why you're using Mathematica.
Right. Yes. Because I think in this integrals, when you calculate this mij, so you have to calculate this like, for example, powers or complicated function. You have to calculate them against the Legendre polynomial, and they do it. So I think that can be simplified quite a bit in Mathematica before putting some numbers. That's what the people who have actually done, like in our group, the people who have actually done this calculation have told me that it has been done. Yeah.
Okay, go on.
Okay, so right. So just to some results. So just some results to just highlight what kind of result that was obtained. Unfortunately, so there is this graph on this paper, but I don't know how to take the picture, but just to say. So what they found in doing so, they found this peaking around this. So they checked out up to Nmax equal to 20 and Lmax equal to 20 for this case of problem. And they took this reason that when they took Lmax, the nearer to Nmax, so like nearer to Lmax equal to Nmax, then the convergence was faster. Of course, it was what they mentioned is this is an observation. So there's no concrete. So for example, there's no reason they could not show that why this is happening. For Lmax less than Nmax, the convergence was actually problematic, and there was some kind of numerical instability they are talking about on very details, and that's what they chose. And I think their suspicion is that you have to, for this kind of numerical stability to occur, this Lmax has to be at least equal to Nmax. Also, but again, what I'm saying is that what I'm reiterate is this, that these are essentially they have observed or they have just run some experiments because they had very strong cluster run experiments something on this to obtain this kind of observation. And a more complicated problem will lead to more complicated kind of numerical stuff. Okay, so what they really they got a peak near MB equals to root 2. So after doing this, what they got, a peak in mod G around, sorry. MB equals to root 2. So somewhat, so M square equals to 2, for example. So somewhat in middle, they found this constraint to happen. So I think it can be interpreted in this fashion that so if you allow for such a pole formation of that kind of cubic coupling is there, then it is so the strongest interaction will try to produce a bound state at MB is like root 2 kind of root 2m kind of mass. So yes, so what they actually got was a plot of data points, and they could extrapolate to find out that it was actually working. So this was actually a problem of cubic coupling. There was also another detailed analysis for quartic couplings, and I won't go into that because I mean essentially so these are the essential numerics that have been done. But of course there are some points, for example, because one needs to think, for example, it's very difficult to, as it is this algorithm is there, I think one should invest some time to understand whether this algorithm can be improved, especially choosing the values or numbers, whatever something, because we really do not have that much of, often we don't have access to that kind of strong cluster systems or something like something that powerful of a cluster. And so if we want to do something similar or better work in a less powerful cluster, then we would like to invest some time into actually trying to understand where we can speed up this whole procedure, what kind of values. For example, can we change this ρm, the way we have chosen this ρm values of the grid, whether that can be changed? Because the precision we cannot tamper with. Ideally, we would have liked to increase the precision, but even let's say we want to put with 1,000 kind of precision, like so whatever we have done, at least in our work, we could not even do this Nmax equal to 20 or Lmax equal to 20 that efficiently. We have done maximally up to Nmax equal to 14 and Lmax equal to 14 kind of stuff. But so because Nmax equal to 20 and Lmax 20 is a literally heavily taxing procedure. So yeah, so I think there should be some investment should be done onto what kind of speed up can be obtained for this kind of stuff. Yeah, that question.
Yeah, so I'm just trying to understand the objective here. So you started off with one coupling constant G square, right? And that corresponds to the 3-point term. And what is the goal? Like you are trying to constrain that coupling, meaning in the parameter space, are you trying to find like what value of G square?
Yes. So there are two. Of course, we are trying to constrain the coupling, but what we are trying to see. So we are taking this spectrum as an input. So we are varying, for example, MB over a range of 0 and 4, and we are trying to see where this coupling with the ansatz and all these constraints satisfying, where this coupling is peaking. So that would mean, what is the meaning of that coupling? That coupling is peaking at certain mass. That means, so it's a at that kind of bound state, that interaction is the strongest. So in some sense, so this is what, and one tries to get some, of course, from that one tries to get some numbers of the root G kind of bound. But I think the main point of this is this maximization.
So how is it different from the renormalization process? Meaning there also we see that coupling constant gets corrected. And
yeah, well, it's I would not say this is it's not corrected, but it's try to finding out that you know because we are not specifying any theory or whatever underlying Lagrangian or something, but we are seeing, we are just taking these minimal constraints, minimal structure and so on and so forth, and with that, of course, we are taking an assumption that we are varying this MB between 0 and 4 or whatever. So we are trying to see that where this interaction is kind of maximal. So I think it's not, well, I don't know. I mean, one thing maybe that we are really not using any Lagrangian to obtain this stuff. It is just from those constraints, this is what is coming out. Of course, it's the simplest stuff.
Yeah, so does it crucially depend on like having only one coupling constant in your theory? Meaning if you had other kind of quartic couplings.
Well, yes. Actually, so for example, like quartic couplings, there's also, for example, a similar kind of study is also done for quartic couplings. There also they do, I mean, they define quartic couplings in terms of actual amplitude. And so then they do the similar kind of stuff over alpha ABC. It seems because this constraint, because so this I was just clear my confusion. So apparently in this constraint, so if you look at this constraint, so let me just go to slide. Yeah, so let me just go to slide number 81. So it is this constraint. So let me just line up. This is the constraint that has been used to that has been, it is the constraint that has to be satisfied with that has to be satisfied over this whole procedure. And in this constraint, so for example, in eta I, the alpha ABCs are also sitting. So it seems that alpha ABC, and alpha ABC is something, I think it's giving the quartic coupling and quartic coupling information. So that is actually making some effect on the on choosing this G square. Only it's I mean it's not clear how that dependence. I talked to people who actually did it, but it's not clear how that dependence is there. I mean, but these presence of these are important, for example, for running the, I mean, for satisfying this constraint. One does not find anything meaningful if you drop those stuff.
Parthiv, I have a question. Like this is like pion scattering kind of problem you are studying. So like you are finding. So is it pion kind of scattering on the study?
Yes. So pion has been studied, for example, using the same framework. And okay, let me go to this slide where I wrote something. Sorry.
No, my question is that, like, is there any physical understanding that why the bound state mass square root 2 there will be or mass square root 2 has any identification with some stable particle in the hadron physics?
So I think, so one thing we know, for example, in so here they assume that there is a bound state. But for pion scattering, there is no, I mean, if you just look at pi naught going to pi naught, that has only, there is no bound state. So people studied pion scattering, so but that is purely a case of quartic coupling, because if you just think that because these are basically interaction between four kind of if you want to see from the field theory, it's like 4 lines are attached to by some interaction. So that is what they do in, they do for pion scattering, the full pion kind of scattering for quartic coupling. This is I would say there is no, so at least in their paper they have not mentioned any physical system, for example, for this example that I told you. I just chose this example easier to explain all the basics, all the important points, important features of this code. But the more interesting is, of course, this quartic coupling on this pion scattering kind of scenario. Okay. Yeah. So so just to there's this detailing of this whole stuff in the respect of, for example, people also did them in respect of pion scattering, and there's a detailed numerical exploration of only in the case of pion scattering. You now have to add the global symmetry, like for example SO3, because there's pi naught, pi 1, pi plus, pi minus, and so there's global symmetries you have to take care of, and this it's a very less cited paper, but it's there in this. So for example, let me just write down. So pion scattering has also been explored. So for example, just see, just get this thing. 9. So it is 18.0. In 10. So this is in this paper they explored pion scatterings in details. Just to mention, this numerics is also, numerical program by itself is not complete, and especially in terms of constraint, what did it use? So let me just, so the numerics. Bootstrap so far just used one, a very simple analyticity properties and unitarity in the simplest possible form. Crucially, and this is very important, they didn't use the elastic unitarity. I mean, the elastic unitarity constraint that one gets when that kind of equality. And I guess so, and I think so. This recent and this elastic unitarity, to be precise, that elastic unitarity and stuffs like Axe theorem kind of stuff, where also this they also did not use. Of course, they also did not use some. That's exhibited by rho st, which is rho st was this double spectral density function introduced, and this actually shows some positivity property in some domains, which has a very important consequence. This is Axe theorem, which tells that there has to be particle production in any scattering, for example, in greater than v greater than equal to 3. So these inputs can be also, I think in my opinion, this includes, I mean, this was first, I think, the whole point of Zibodov's recent paper on S-matrix Bootstrap, where he basically sets the stage of using these elastic neutrality or these kind of properties into the current numerical bootstrap. And by using this, one possibly will be able to constrain more. I mean, the kind of problem that is the current constraining that is there, one will be able to constrain more the space of S matrices. Some interesting observation that has been obtained, just to point out. So, for example, from so far, and these observations are interesting. See, this numerical bootstrap essentially uses some notions of positive semi-definiteness like safety bootstrap. The positivity of safety bootstrap has been recently explored by in context of positive geometries. So one wonders what sort of, or whether similar stuff can be done for numerical S-matrix bootstrap. And finally, just there seems to be an observation that interesting theories like chiral perturbation theory lies on the boundary of the region of allowed S matrix, and this is quite reminiscent of interesting quite interesting interesting CFTs residing kings. So question, and in particular this kink in CFT bootstrap can be explained by positive geometry. So one wonders whether that boundary observation also underlies some positive geometry explanation. So just to summarize that, there seems to be an observation that interesting theories like for pions, for example, chiral perturbation theory, which is usually used to calculate various parameters related to pion scattering, they seem to lie on boundary of the region of allowed S-matrix if you follow this kind of bootstrap program. Now, this is almost quite reminiscent of the CFT bootstrap, where interesting CFTs like 3D Ising model or something like that, they seem to reside in kinks in the space of the allowed CFTs. And in fact, the positive geometry work that I was just talking about in connection to CFT bootstrap has actually given some indication or some kind of explanation, if not full explanation, but some at least intuition as to why interesting theories may live on kink. So one can wonder that whether similar kind of expression, a similar kind of positive geometry explanation can be given these kind of boundary observations that we are getting. However, I must warn here that these observations in S-matrix bootstrap, in my opinion, are still incomplete, and some more exploration needs to be done before coming to any kind of definite conclusion and then proceeding further to explanation. Because in contrast to CFT bootstrap, even numerically S-matrix bootstrap is not that explored that vigorously like the CFT bootstrap is explored. Okay, so in these words, I want to finish the traditional bootstrap study. This is what has been done, kind of stuff done. I just want to, in this remaining 20 or 25 minutes, I want to discuss a small direction about S-matrix. This is not exactly bootstrap, but what I would like to call this is something that we are, of course, it has been made connection with bootstrap, but so this is my personal interest, something that I want to do or I want to explore is it's more, in my opinion, still now it's more utopian, but I think there is some hope. So just to, this exploration is what you can say, this is so it's essentially quantum information theoretic explorations of S-matrix. So usually, so far, I mean, if you see predominantly the quantum information theoretic stuffs that has been done in respect of high-energy physics, like they have been explored heavily in fields like holography and all this kind of stuff. And people study various quantities, like various kinds of entropies, or these recent ideas of complexity and all these things. They do this kind of stuffs mostly in the position space or configuration space. Now there are some marginal works. I mean, this is something we are not new, but there are some marginal works where these QI quantum information theory quantities were computed in momentum space, like scattering or something like that. So let me just tell you one such reference just to point out. So this is in these reference, what they do, they basically study variation of entanglement entropy in scattering process. So just to initiate what these people do is this. So they start, of course, there are 2-2 scattering. They consider 2-2 scattering. But they start with a pure state, of course. So start with some pure state, let's say PA and PB, pure momentum state, and then of course evolve with respect to with S, and that gives the final state. But then they assume that the final state can have actually, apart from the same 2 particle state, it can have some inelasticities as well. It can have some inelasticities as well. That is why what they do, they actually project this. So they construct a final state by projecting this state on these 2 particle states. See, this is different. So while the initial state is a pure state, the final state is not. The final state is not really a pure state. And then these people calculate, so they construct, let's say, a reduced density matrix, let's say rho A, by tracing and F is not automatically normalized. So they construct this rho A trace. So for example, tracing the B particle, and then they calculate the entanglement entropy, the corresponding entanglement entropy. So they calculate using this thing, calculate the entanglement entropy. And of course, what is found that scattering, as a result of scattering, of course, there's a positive entanglement. I mean, of course, entanglement entropy, entanglement increases because scattering creates an entanglement in the momentum variable of the outgoing particles. So in that sense, so this is a hint. This is a very important hint to me, at least, that of course scattering processes information, processes QI, and in particular S-matrix acts as a processes QI processing. But that gives me that wonders me a question, that whether one can develop a for quantum algorithm for simulating QFT non-perturbatively in terms of S-matrix. What I mean by this is that if you look at the usual Hill Jordan, if you look at the Hill Jordan Preskill algorithm for simulating scalar field theories, then you will see that that algorithm is based on a Lagrangian, and specifically they use this algorithm to simulate a 5-4 theory. Now what they do, they put this 5-4 on a lattice and then they try to simulate this thing. In particular, they use a Lagrangian to, the key point of their algorithm is that they do a Lagrangian to have this algorithm. But question is that, is it that you have to have a Lagrangian for simulating a quantum field theory in a quantum computer? Is having a Lagrangian a must? Is it not possible to simulate a quantum field theory or processes in quantum field theory without having to resort to a Lagrangian and underlying Lagrangian? So in a sense, is it possible to simulate an S-matrix in its full extent? But that would mean that one has to understand the more QI theoretic properties or more QI theoretic properties of the S-matrix. In particular, what does this various analyticity structures or whether these analyticity structures of this S-matrix can be understood in some in QI theoretic framework. Also, I would be very happy actually. So the same authors, they show that this simulation of scalar field theory is a BQP, they belong to BQP complexity class. So, which is of course a bounded quantum polynomial complexity class. But I will be interested, but again, they use this explicit Lagrangian and do this stuff. But can we prove this without going into Lagrangian, some abstractly or starting from an S-matrix point of view, that any algorithm that a quantum algorithm that tries to simulate a process described by a certain S-matrix or having these properties, these essential properties, that algorithm has to be in the BQP complexity class. So the clear-cut question that we can ask, that whether starting from the properties of S-matrix, one can show or one can prove that any algorithm, quantum algorithm that tries to simulate such an S-matrix has to belong to a BQP complexity class. And another aspect that I want to that is worth investigating along these lines, why this kind of scattering, why QI information is actually still is my thing, that can one derive, for example, Frossard bound using QI theoretically? And why do I suspect that such thing can be possible is for a simple observation. So let me go to the next slide, that the elements of Frossard bound, the reason that Frossard bound actually appears is because of polynomial boundedness, but more crucially, that manifests itself into an effective truncation of partial wave sum. So due to this polynomial boundedness, you can actually effectively truncate this partial wave sum of the amplitude, the imaginary part of the amplitude, to a particular L max value. So this L equal to 0 to infinity, you can actually replace this L equal to 0 to L max. So one of the first point would be to understand, and I think that there should be a possible, and that there should be there will be an L max can also be understood from some heuristically from semi-classical argument that if you have a finite range potential, you will have L max will be cut off. But my suspicion is that one can also try to obtain an quantum information theoretic understanding that why this L partial sum can be cut off. So it seems that all these partial waves up to L max are behaving in a certain coherent way, while the rest of the rest of the partial waves are not really joining in the process. So can we give a QI theory? So final question is that, can we give QI theoretic explanation to this? So all of these are, I would say, rather speculations, but in my opinion, these are worth visiting, and especially given that the exploration of quantum information theoretic quantities in momentum space is very scarce. I mean, whatever has been done is it's always in the position space. I mean, in holography, mostly in the position space. So I personally think that one should, and I mean, it is worth a shot to actually explore this thing in the momentum space. So yeah, saying this, I would.
Can you please tell why it is difficult to study information theoretic things in momentum space?
Well, I don't know. I mean, I do not know. Okay, one thing is that I would not say difficult, but it seems that nobody have done this. I mean, very few people have actually done it for some reason. I do not know. I mean, I don't see a very prominence present. I mean, at most you can think of like 4 to 5 only. I think there can be 5 to 6 papers at most. You will find out which actually discusses for example, entanglement entropy or something like that for scattering particles. I don't know why such thing. Of course, there's a problem of infinity comes, but that can be handled with, because this is infinite space-time volume. But I don't know why people have thought about this. It seems to be very weird to me. Is it some inherent difficulty or no? Yeah. I mean, some people have also tried to calculate. I think there was one paper by Vijay Balasubramaniam that who has also tried to calculate this entanglement entropy in the context of not only just particle scattering. So there is one attempt, but also I think in string scattering also they have tried to do some. He had tried to do some explanation. So I saw a paper which basically, but yeah, I'm not very sure that why there is not enough exploration.
So Parthiv, since you talked about the final states of the S-matrix being entangled, so
yeah.
Does it violate any the unitarity condition of the S-matrix?
No, no. Why? Well, we're not.
Okay, no. I was trying to
well,
so this S dagger S equal to 1. So
yes,
S matrix will be like a unitary evolution.
Yes. So
in that way, all the properties of S matrix is preserved here.
Can I make a comment?
Yeah.
I think like the S dagger S statement is that like when you will sum over all possible final state particles, then it will be identity. But he is constraining probably that only external particles 2 particles. That's why this becomes seems like it is violating unitarity. But if one sums over all particles in the final state, probably one will again get a pure state. Is it true?
Yeah. Well, maybe. I mean, yes, you have actually right. So but I've not thought about it. But yeah, why that is? But I think
I think Arnab pointed out that like the S-matrix, like it's a unitary evolution S-matrix, right? So
yes.
Really, one should get also pure
yeah,
state.
right.
Yeah.
Yes. I think you are right, because so for example, this so this SPAPB is the whole state, but we are not so this is a final. I mean, this is not the final state, the final target state, but it is the state evolved by S. But this is not the state with whose we are taking the entanglement entropy. We are just projecting to a 2-particle state. So maybe in doing so here, we are actually considering that there will be even more states apart from just those 2-particle states. So yeah, I think if you consider those states as well, it will be.
So probably is it like you have many final states, but you are just considering only 2 final states and entanglement between them.
Yeah, right. So we are actually considering that. So like we are starting with 2 particles, but there can be, so there will be definitely those 2 particles and many other states, like other kind of states will be there. But we are just trying to see that we are just trying to see that what happens to the two particles, just to focus on those two particles as a. But yes, you're right actually. So I think that explains that the other particles, if you just take into consideration.
Then can I make a statement? I think similarly, then if the S value, which is the Mandelstam value, if that you constrain, say from 4m square to 9m square kind of thing, then probably you would expect that the final state will be also, like if you consider only two particle states, then it may be a pure state. Well, it will exhaust all the possibilities, and it may be a pure state or not.
Yes. This is actually a good idea. Yeah, this we have never thought. Yeah, you are actually right. So when we are within that domain, that that domain, I'm pretty sure that it should be. Yeah. So that we just I've not thought about it, but yeah, it seems to me. Right.
And you also mentioned about the inelasticity in this 2 going to 2 plus x.
Yeah. So I've chosen this x2.
So I'm not understanding that. So is it due to this inelasticity that you are getting an entangled state, or if you did not have this inelasticity, like would you still have entanglement in different states?
Well, yeah. So for example, how to put it? So we are here. So I think from the setup, it's we have also not thought about this. These questions are very important. That if so, whatever I have seen, this x is so there is always an x, so that it's actually projecting to some this kind of a momentum, that kind of state. So it's always done with respect to the fact that there is some x, but we are just projecting onto the smaller subspace, and we are calculating entanglement. But I think this idea is good, that we have really not seen that when there's strictly 2 going to 2, just like this elastic notative domain, what actually happens. Yeah, I think we should try to think about that.
So Subbu has a question in the chat. Would you like to ask Subbu?
Yeah, I mean, with all this discussion, I'm slightly confused. So F is a pure state, right?
No, F is not a pure state.
I see.
F has a superposition over all the QA/QP.
So that is still a pure state. F is a ket vector, right?
Yeah, F is a ket vector, but the way so
if you write a ket vector, that's always a pure state.
No. So okay, fine. So I mean, I have not written. So the ket vector is okay. The way I've just denoted by that some state. Just. Yes. Yeah, right. F is actually.
What I see in the slide is that you have taken F, which is a pure state, and then you have traced over B. And if you trace over like a subsystem of state, you will get a mixed density matrix if it is an entangled state. But I don't think you are going from like a pure state to a mixed state. So there is no, I don't see any contradiction with unitarity. I mean, I might be wrong, but you can correct me.
Yeah. F is actually a pure state. You're right. F is, because this is thing, right. F is a pure state. Yeah.
Okay, Biswajit has some comment, like projecting in F, projecting to what in F?
I think it just means the tracing out.
Tracing out, of course, but that is just a way to compute the entanglement entropy, right?
Exactly.
Okay.
Okay, I think before we take any further question, we should all unmute ourselves and thank Parthiv, not only for this lecture, but for his entire series of lectures. So please unmute yourself. And we have some time for questions, so people can go ahead and ask.
Parthiv, like I
Yeah.
got a question. I think like probably you had studied in your work also. Like I think if when one constrained a region of space theories, so like they are probably like to get that one of the theories how far how much different from other theories. Probably one can compute relative entropy between
Yes,
them
yes,
and can
yes,
get.
yeah,
So
yeah.
can you
So
make
I've
some
actually,
comment on this?
yeah. So basically, we did this. Like, I mean, there's this hypothesis testing that can be done using this relative entropy. So there are two uses. So relative entropy can be used two ways. One is that you can consider relative entropy of two different states, and I mean relative entropy can be measured to distinguish, used to measure the distinguish between two states, or it can be actually used to what they call the hypothesis testing. So that also can be used. That means you take for the same quantity and you take with respect to two different theories. I think in our section on that hypothesis testing, what we tried to show, for example, suppose you have so for example, there's a let's say I have a pi scattering, pi naught going to pi naught going to pi naught. So it's essentially a quartic kind of quartic interaction. So whether it is, so there is chiral perturbation theory. So chiral perturbation theory can be used to explain numbers. Also, one can try to see whether phi4 can be used to describe that. Of course, here phi4 meaning it's a one loop phi4. We did not consider the entire like all phi4. It's a one loop phi4. So what we did is we did some hypothesis testing, to see that for that kind of what we observe, in order to explain that how much phi4 and chiral perturbation are actually different from each other. So or in the sense that in the theory space how closer they are. So that is what the hypothesis testing we actually sort of thought. But I would say that this is hypothesis testing is that section is very immature, and I think more exploration is needed. So more things needed.
Okay, thanks.
Any further questions or comments? Okay, so if not, let us thank Parthiv once again. Okay, so before we stop the session, from behalf of the entire organization, I would like to say a few words. It's a vote of thanks, if you like. So first and foremost, we need to thank three people whose hard work, actually, we never got to see the output of their hard work. And these are the three faculties at the IIT Kanpur String Group. Arjun Bakchi, Nilay Kundu, and Nitarko Das. They actually played a pivotal role in ensuring that IIT Kanpur was a venue for ST4 2020. They worked really hard. They helped us a lot. In fact, it's not an overstatement to say that they were extremely crucial and essential in ensuring that we got IIT Kanpur as a host. And to add it to that, a lot of facilities which we couldn't have asked for ourselves, but they gave it to us nonetheless. So I will ask all of you to give a big round of applause to these three faculties. So next is, of course, once IIT Kanpur got finalized as the venue, we got to our local organization committee, and their effort also we never got to see come to fruition. But I would like to thank them nonetheless. Pinaki, Kedar, Mangesh, and Puneet, they promptly agreed to help us, and Puneet actually was part of our ST4 organization group, and he continued for the last 3 months being part of the organization team. So a big thank you for all of them. And next, we would like to thank all the speakers. When we contacted the speakers after the phase 2 votes came in, there was still a lot of doubt that whether the event will be held offline or online. And we were frank about this dilemma, and they were understanding of that fact from the very beginning. They acclimatized to this rapidly changing scenario very well. They adapted, they prepared in these difficult circumstances, and I think we had marvelous set of lectures on 5 topics by 7 speakers. So a big thank you to all of them. And of course, last but not the least, to all the participants, to the 100-odd people who seems to have joined Slack, and to the 50-odd people who actually remained actively participating on the lectures. But I should also mention that there were several people who could not join in the lectures because of poor connectivity, but they kept on watching it on YouTube. All the lectures videos uploaded so far have garnered over 93 hours of view time. And that proves that people have been following who couldn't follow it live over Zoom. So that's a great bonus for us. And thanks to all the participants, wherever you are, in whatever circumstances you are, we wish you continue to be in good health. And thank you for joining us. So a big hand to all of them as well. And I guess if anyone has anything else to say, they can go ahead. Otherwise, we will close the session.
Okay, I mean, I think I have like harassed Madhu on chat, so he is not coming up to say this. So let's thank all the organizers. It must have been really hard in these situations and also in the setting to conduct the workshop. And we are all academicians. We are all active in ST4, but of course, like it's just the organizers who make it possible. And it's very important, and they paid so much attention to everything. So let's thank the organizers by giving a round of applause.
Okay, thank you, Subbu, for those kind words. And okay, so this is the end of ST4 2020. It was nice knowing you all and talking to you all. And we will see over LET HEP forum. And if not, we will definitely see each other on next year. So a big goodbye to all of you.